We've always trusted our eyes. For thousands of years, we built our understanding of the universe on what we could see: stars twinkling, planets moving, the moon waxing and waning. But the cosmos doesn't play by our rules. And long before we realized it, the universe had already hidden most of itself. What if I told you that everything we've ever seen, every star, galaxy, cloud of gas, and burst of light, makes up less than 5% of what actually exists? The rest is something we can't touch, can't see, can't hold in our hands. But it's there, all around us. Scientists call it dark matter. The name sounds ominous, but it's more of a placeholder, a way to describe a kind of mass we know must exist, even though we've never seen it directly. It doesn't glow. It doesn't absorb light. And yet, it bends space with its gravity. It was the galaxies that betrayed it. In the 1970s, astronomer Vera Rubin made a discovery that changed everything. She measured how fast stars orbited around the center of spiral galaxies, expecting the outer stars to move slower, just like the outer planets in our solar system. But they didn't. They moved too fast, as if something invisible was holding them in place. This something couldn't be made of normal atoms. It didn't emit light. It didn't block stars behind it. But it pulled on everything with gravity, as if every galaxy was wrapped in a halo of hidden mass. And not just galaxies, entire clusters of galaxies seem to weigh more than they should. Their gravitational pull is stronger than all the visible matter can explain. Something unseen is holding it all together. We can't see dark matter, but we see what it does. It curves the paths of light. It holds galaxies in their shapes. It formed the very scaffolding on which stars and planets would one day appear. So we began to map it, not directly, but by its fingerprints, its tug on the visible, its silent structure beneath the light. We stepped into a universe that is mostly invisible, and this was just the beginning. When we look up at the night sky, we see stars scattered like grains of sand, random, isolated, endless. But zoom out far enough, far beyond the Milky Way, beyond nearby galaxies, past the local cluster, and a different picture begins to form, one that looks almost biological, a structure, a shape, a cosmic web. Galaxies are not scattered evenly across space. They gather in threads, massive filaments, stretching hundreds of millions of light years. Between these threads are voids, vast dark regions with almost nothing inside. The result is a universe that resembles a sponge or the branching of neurons in the brain. This structure wasn't drawn by hand, it was carved by gravity. and at the heart of it is dark matter. In the early universe, shortly after the Big Bang, matter wasn't evenly spread. There were tiny fluctuations, denser spots where gravity pulled harder. These became the seeds. Over billions of years, dark matter gathered around them, amplifying their gravity, attracting more mass, forming filaments. Gas followed, then stars, then galaxies. The visible universe as we know it formed along the skeleton laid out by dark matter. Today, massive simulations, like those run on supercomputers at NASA or the Max Planck Institute, recreate the birth of this web. They start with just two things: dark matter and physics, and yet, after billions of simulated years, they reproduce something that looks astonishingly like the real universe. When telescopes like James Webb peer into the distant past, looking billions of years back, they see galaxies already forming along these filaments. Even then, the scaffolding was in place. But we didn't just discover the web, we began to trace it. Surveys like Sloan Digital Sky Survey, SDSS, mapped over 1 million galaxies in 3D. The results were breathtaking, not a flat sky, but a honeycomb with walls, strands, and empty bubbles. It turns out the universe is not a smooth expanse. It is structured, wired, woven together by gravity and time. And the blueprint wasn't made of stars. It was made of something invisible. Once we accepted that something invisible was shaping galaxies, the question became, how do you study a thing you can't see? The answer came from an unexpected place, not a new telescope, but a century-old idea from Albert Einstein. According to his theory of general relativity, gravity isn't just a force. It's a curve in the fabric of space-time itself. Massive objects like stars or galaxies warp space, bending the path of anything that moves through it, even light. And when light bends, strange things happen. Imagine a distant galaxy sending light across the universe. If something incredibly massive, like a cluster of galaxies, sits between us and that faraway object, its gravity bends the light coming past it. The result? A cosmic lens. We call it gravitational lensing. Sometimes, the background galaxy appears stretched into arcs. Sometimes it becomes a ring. Sometimes it's copied, appearing in multiple places at once. But in all these cases, what we're seeing isn't the object itself. It's a bent version of it, distorted by gravity. Einstein predicted this, but he thought we'd never be able to observe it. Then, in the late 20th century, we did. Gravitational lensing became one of the most powerful tools in modern astronomy, not just to study distant galaxies, but to reveal the invisible mass that was doing the bending. Because the more distorted the image, the more mass there must be behind the lens. and very often there wasn't enough visible matter to explain it. So what was bending the light? Dark matter. Using gravitational lensing, astronomers began mapping where the hidden mass was, not by looking for it directly, but by tracing its influence. Every warped galaxy was a clue, every arc a signature. Even more remarkable is something called weak lensing, subtle distortions across wide regions of space. With enough data, scientists can build a statistical map of the universe's invisible structure, revealing the cosmic web that links galaxies together. In a strange twist, gravity, the thing we thought would hide the invisible, became the thing that made it visible. It turned space into a lens. It turned mass into a signature, and it gave us a way to see the bones of the universe. What we found next was that this web of gravity wasn't just everywhere, it was everything. Sometimes the universe whispers, other times it shouts. In 2007, astronomers studying data from a radio telescope in Australia found something they couldn't explain. It was a burst, a powerful spike in radio waves that lasted just a few milliseconds, but it carried the energy of hundreds of millions of suns. And then, just like that, it vanished. At first, many thought it was a glitch, a cosmic hiccup, an error in the system. But over time, more appeared, different telescopes, different parts of the sky, and always the same thing, a sudden, sharp blast of radio energy. So fast it was easy to miss, so powerful it couldn't be ignored. They became known as fast radio bursts, or FRBs. Each one comes from a different corner of the universe. Some are one-time events, others repeat, like a cosmic heartbeat, irregular but persistent. But their origin remains one of the great modern mysteries in astronomy. What causes them? We've ruled out the mundane. No, they're not aliens. Probably. The leading theories involve neutron stars, incredibly dense stellar remnants, some with magnetic fields trillions of times stronger than Earth's. When these magnetars shift or crack under their own stress, they could release energy in a burst. Another theory suggests collisions between stars, between black holes and neutron stars, or even between exotic particles. Some FRBs are so far away that their signal has traveled billions of years to reach us. And that's part of what makes them so valuable, because as these signals travel, they pass through space, and not empty space, but space filled with plasma, gas, dust, and invisible mass. Each FRB becomes a probe, telling us something about the structure and content of the universe along its path. Like sonar pings through an ocean we can't see. NASA, along with observatories like CHIMES and ASCAPs, now listens constantly, Some bursts are even used to estimate how much missing matter is floating between galaxies, matter that doesn't glow but slightly alters the signal as it travels. In a way, FRBs are like messages from the dark. We don't always know who's sending them. We don't always know why. But we know they come from far away and from something powerful. And the more we listen, the more the dark speaks back. Every second, trillions of tiny particles pass through your body, through your skin, through the earth beneath you, even through mountains. You don't feel them, you don't see them, and yet they are everywhere. These are neutrinos, often called ghost particles. They were first proposed in the 1930s to solve a puzzle. Physicists had noticed that in certain radioactive decays, energy seemed to vanish. That violated one of the most sacred rules in physics, the conservation of energy. So Wolfgang Pauli suggested that an invisible particle was carrying away the missing energy. A particle so small, so light, and so indifferent to matter that it could slip through solid walls, through entire planets, without ever touching anything. That was the neutrino. Decades later, we confirmed they were real. And stranger than we imagined, neutrinos have almost no mass, just a whisper of weight. They don't carry an electric charge, and they interact with matter only through the weak nuclear force, one of the rarest forms of interaction in the universe. To catch even a single neutrino, you need patience and creativity. That's why the Ice Cube Neutrino Observatory was built in Antarctica. There, beneath the South Pole, scientists buried thousands of sensors in a cubic kilometer of clear ice. When a neutrino does happen to strike an atom, it creates a tiny flash of light, a signal that something invisible has briefly made itself known. Neutrinos come from everywhere. They're created in the sun, in supernovas, in the collision of stars. Some come from cosmic rays hitting Earth's atmosphere. Others come from the very edge of the observable universe, born in the violent cores of galaxies. And because they travel almost entirely unimpeded, they arrive unaltered. Unlike light, which can be bent or absorbed, neutrinos carry clean messages from the most extreme environments. They're like messengers from creation. Some theories even link them to the mystery of dark matter, or to why the universe exists at all, why matter wasn't canceled out by antimatter in the early moments after the Big Bang. We don't fully understand them, but we know this. They are part of the invisible story. They pass through us endlessly, and they may carry the key to the deepest questions we've ever asked. We often imagine space as cold, and it is, but there's cold, and then there's the coldest. Most of the universe floats just above absolute zero, the lowest possible temperature, where all motion in atoms theoretically stops. That's minus 273.15 degrees Celsius, or 0 Kelvin. But even the vacuum of space isn't quite that cold. Thanks to the leftover glow of the Big Bang, space has a background temperature of about 2.7 Kelvin. Still, there are places colder than that, and some of them are not natural. Let's start with the coldest natural places. Dark nebulae, like the Boomerang Nebula 5,000 light years from Earth, are colder than the background of space itself. There, gas expands so quickly that it cools below 1 Kelvin, colder than anywhere else known in the cosmos. Why does that matter? Because at these temperatures, atoms behave differently. They slow to a crawl. Molecules struggle to form. Chemistry changes. It's like pressing pause on the physics we know. But even that isn't cold enough for us. On Earth, physicists have created colder temperatures in laboratories, even approaching nanokelvins, billionths of a degree above absolute zero. Using magnetic traps and laser cooling, they've slowed atoms until they almost stopped moving. Why? Because at these ultra-low temperatures, matter reveals its quantum behavior. Atoms act like waves. Multiple particles can behave as one. Entire systems enter exotic states, like Bose-Einstein condensates, where thousands of atoms share a single quantum state, essentially becoming one superatom. It's not just a physics experiment. It's a window into the early universe. The very first moments after the Big Bang were governed by quantum laws, and by understanding how matter behaves when slowed to the edge of stillness, we gain insight into how everything may have started. Even in space, humans have tried to go colder. NASA launched the Cold Atom Laboratory aboard the International Space Station, a tiny facility that studies quantum particles in microgravity. There, scientists can observe behavior not possible on Earth, unlocking new insights into gravity, time, and the nature of reality itself. The coldest places in the universe aren't just places of emptiness. They are places where physics whispers secrets, where motion fades and new laws begin to emerge. We talk a lot about stars, galaxies, and black holes, about what's there. But sometimes what's not there is just as important. The universe is not a crowded place. It's not a wall-to-wall fireworks show. In fact, most of it is astonishingly empty. These regions are known as cosmic voids, vast stretches of space where almost nothing exists, no galaxies, no stars, sometimes not even gas, just dark, quiet distance, and they are enormous. Some voids are hundreds of millions of light years across. To imagine them is to imagine silence, not just in sound, but in light, matter, motion. Entire galactic clusters sit around their edges, like cities bordering a desert no one has crossed. But these voids aren't mistakes. They're part of the structure. As we saw earlier, the universe is shaped like a web, with filaments of galaxies forming threads and intersections. The space between those threads, that's where the voids live. They're not holes in the fabric of space. They are space where gravity never gathered enough matter to build. And because of that, they offer a unique perspective. In voids, the rules bend. There's less gravity pulling on matter, less interference from stars or radiation. That makes them ideal laboratories for testing the laws of physics on grand scales. Even the expansion of the universe behaves differently inside them, sometimes faster, sometimes slower. Some cosmologists believe voids could help explain dark energy, the mysterious force accelerating the universe's expansion. By observing how galaxies move around and inside voids, we might catch a glimpse of what's driving that cosmic push. Voids also offer clues about the early universe. Their size, shape, and distribution reflect how matter clumped, or didn't, after the Big Bang. Studying them is like looking at the negative space of creation, and in some cases, the emptiness is so extreme it creates anomalies. One famous example is the cold spot in the cosmic microwave background, a region colder than expected, possibly linked to a massive void. Some speculate it might hint at something deeper, a flaw in our model of the universe, or even contact with something beyond it. In the end, cosmic voids remind us that the universe isn't made of just things. It's made of space between things. And sometimes that space is where the mysteries live. Look up on a clear night and the stars seem endless. But in truth, there's a limit to how far we can see. A boundary, a horizon. Not because space ends, but because light takes time to travel, and the universe has only existed for about 13.8 billion years. That means the farthest light we can receive is light that's been traveling for 13.8 billion years. But here's the twist. Because the universe has been expanding, the most distant objects we can see today are actually about 46 billion light years away. That's the edge of the observable universe, a sphere around us filled with galaxies stretching nearly 93 billion light years across. Beyond that, we don't know. We can't know. Not yet. The light hasn't reached us, and in some cases, it never will. The fabric of space itself is stretching faster than light can cross it, meaning parts of the universe are slipping away, permanently beyond our reach. But even within that bubble, we can see astonishing things. The oldest light in the universe, the cosmic microwave background, is the afterglow of the Big Bang. It's not a reflection or a shadow. It's the actual light, cooled and stretched over billions of years. We see it in every direction, like the walls of a cosmic cave. And then there are galaxies, tiny smudges of red on deep field images taken by James Webb or Hubble. These are not close. They are not even recent. Some of them formed just a few 100 million years after the Big Bang. We're not seeing them as they are, but as they were. Ancient light arriving now, a delayed message from the dawn of time. And the farther we look, the younger the universe appears. So what lies beyond the edge? More galaxies? An infinite expanse? A loop? A wall? Something we can't even imagine? We don't know. All we can do is look deeper, build better instruments, and follow every faint photon to its source. Because when we stare at the edge of the observable universe, we are not just looking far away, we are looking back in time. Imagine flipping a coin 1,000,000,000 times, and it lands on heads every single time. That's the kind of imbalance we're talking about when it comes to the early universe. Because when the universe began, in that first unimaginable instant after the Big Bang, it should have created equal parts of two things: matter and its twin, antimatter. For every electron, a positron. For every proton, an antiproton. They're mirror images, same mass, opposite charge. And when matter meets antimatter, they annihilate, releasing pure energy. So here's the problem. If the universe began with equal amounts of both, they should have canceled each other out. Everything should have turned into light. No galaxies, no stars, no planets, no us. And yet, here we are. Something tipped the balance. For every billion antimatter particles, there were 1,000,000,001 matter particles. And when all the pairs destroyed each other, that tiny surplus, just 1 in 1,000,000,000, is what remained. That one is everything. It's what formed every atom in your body, every tree, every mountain, every star. But we don't know why it happened. This puzzle, called the matter-antimatter asymmetry, is one of the deepest mysteries in physics. It suggests that somewhere, in the earliest moments of time, matter and antimatter were not treated equally. Something broke the symmetry. And scientists are still searching for the cause. Experiments like those at CERN's Large Hadron Collider or in underground neutrino detectors are hunting for clues. One theory, called CP violation, suggests that certain particles decay just a little bit differently than their opposites, just enough to create that imbalance. Others look to neutrinos, which might be their own antiparticles, a strange idea that could rewrite the rules of particle physics entirely. And still others wonder, is there a part of the universe where antimatter won? A mirror cosmos, invisible to us, separated by more than space, separated by history. We don't have the answer yet, But the fact that there is a question at all, that anything survived to ask it, is already a kind of miracle. We can't see them, not directly, not with most telescopes, not even with the sharpest eyes in the sky. And yet, we've found them, thousands of them, exoplanets, worlds orbiting other stars. How do you find something you can't see? You look for its shadow. In 1995, astronomers discovered the first confirmed planet outside our solar system, a giant, blistering hot world orbiting dangerously close to its star. Since then, we've found rocky planets, ocean worlds, gas dwarfs, and frozen giants, many nothing like anything we see around our sun. But we rarely see the planets themselves. Instead, we detect what they do. The most common method is called the transit method. When a planet crosses in front of its star, as seen from Earth, it blocks a tiny fraction of the star's light, just a dip in brightness, sometimes less than 1%. But if it happens regularly, like clockwork, we can infer there's a planet there. And from that flicker, we can learn astonishing things. We can estimate the planet's size, its orbit, and even, in some cases, the composition of its atmosphere. When starlight passes through the edge of a planet's atmosphere, it changes slightly, leaving fingerprints of gases like hydrogen, water vapor, methane, or carbon dioxide. That's how we found K2-18b, a world more than 100 light-years away that shows hints of water vapor and perhaps even more complex chemistry. Other methods detect the wobble of stars, pulled by the gravity of orbiting planets, or use gravitational microlensing, where a planet's mass bends and magnifies background light like a lens in space. The James Webb Space Telescope is pushing this hunt further. With its sensitivity to infrared light, it can peer through dust, detect cooler planets, and even start building rough profiles of their atmospheres. And every new discovery raises the same question. Are we alone? We don't know yet, but we know this. There are more planets than stars in the galaxy, and every time we catch a shadow, we're catching a possibility. Galaxies are not peaceful islands. They are giants in motion, and sometimes they collide. Over billions of years, galaxies don't just drift. They fall toward one another, pulled by gravity across unimaginable distances. When they meet, it's not a gentle encounter. One devours the other. This is called galactic cannibalism. It happens more often than you might think. In fact, the Milky Way, our own galaxy, has been eating smaller galaxies for billions of years. Evidence lies in the form of stellar streams, long trails of stars pulled from shredded dwarf galaxies, still orbiting the Milky Way like ghostly fingerprints. And it's not finished. Right now, the Milky Way is on a slow-motion collision course with Andromeda, the nearest large galaxy. In about 4 billion years, the two will merge. Stars will fly past each other, rarely colliding, but dramatically reshaping their orbits. Over time, the two spirals will melt into one massive elliptical galaxy. But why does this matter? Because these collisions shape the universe. They drive star formation, trigger black hole activity, and determine the architecture of galaxy clusters. Without them, the cosmos would be quieter and far less complex. In some cases, the smaller galaxy is completely absorbed. In others, remnants survive, distorted cores, tidal tails, or regions of intense starbirth known as starburst galaxies. Sometimes, even the central black holes of merging galaxies collide. These events are so violent they send out gravitational waves, ripples in space-time now detectable by observatories like LIGO and Virgo. And these aren't ancient relics. They're happening now. The Magellanic Clouds, two dwarf galaxies orbiting the Milky Way, are being stretched and stripped by our galaxy's pull. Eventually, they too may be swallowed. Galactic cannibalism reminds us that space is not static. It's a realm of motion, tension, and slow violence. Structures change, borders dissolve, even giants can be consumed. It's not destruction for its own sake. It's transformation on a cosmic scale. And every time galaxies merge, the universe becomes a little more tangled and a little more alive. They're supposed to be anchors, massive, immovable, sitting at the center of galaxies, pulling everything inward. But what if a black hole moves? Not drifts, not orbits, but launches itself through space. It sounds impossible, and yet astronomers have found black holes doing just that, hurtling through galaxies, trailing stars, and gas like cosmic cannonballs. These are called recoiling black holes, and they're among the strangest consequences of cosmic collisions. Here's how it works. When two black holes spiral into each other, like those at the centers of merging galaxies, they don't just combine, they send out gravitational waves. And if the waves aren't emitted symmetrically, if the black holes are spinning differently or have unequal mass, the resultant wave kicks the merged black hole hard. In some cases, fast enough to escape the galaxy entirely. We're talking speeds of several thousand kilometers per second, enough to outpace the gravitational grip of a galaxy that spans hundreds of thousands of light years. Imagine that. A black hole, millions of times more massive than the sun, flung into intergalactic space. Invisible, except perhaps for the trail it leaves behind, a jet of light or a cloud of torn stars. But even within galaxies, black holes can wander. Some galaxies show signs of off-center cores, where the expected supermassive black hole isn't at the center but offset by tens of thousands of light years. Others contain multiple black holes, evidence of previous mergers where the cores haven't yet settled. Those wandering giants affect more than just their immediate surroundings. They can stir star formation, distort orbits, and even impact the evolution of galactic structure. And then there's the question, how many are out there, roaming? We might never know, because without feeding, without a disk of glowing matter, a black hole is invisible, undetectable, unless it crosses paths with something else. But just knowing they're out there, these silent travelers, flung from violent beginnings, adds a new layer to our understanding. Black holes don't always sit still. Sometimes they run. They don't look like galaxies. They're not supernovas, and they don't fit any known category. They're just rings, glowing radio bright circles floating in the sky, massive, mysterious, and totally unexpected. These are called odd radio circles, or ORCs, a term as strange as the phenomenon itself. The first ORC was discovered in 2019 by a team of astronomers using an Australian radio telescope. It appeared as a perfect circle, several arc-minutes wide, larger than the full moon, but invisible in optical light. It only showed up in radio wavelengths. At first, scientists thought it might be an artifact, a glitch in the data. But then they found another, and another, and another. Each one was a huge, faint halo. Some surrounded distant galaxies. Others floated seemingly alone. They weren't supernova remnants, too large, not galaxy clusters, too round, not lensing effects. The light wasn't bent. They were just there. Each ORC spans hundreds of thousands of light years, maybe more. Some appear to have a galaxy at their center, others don't. Some have irregularities, but most are shockingly symmetrical, a trait that only deepens the mystery. So what could they be? One theory suggests they're the result of massive explosions, perhaps from supermassive black holes suddenly releasing jets of energy in all directions, like a shock wave. If that's true, we might be seeing that echo of ancient activity, a bubble still expanding through intergalactic space. Another idea proposes a galactic collision or merger where violent interactions sent matter outward in a vast circular front, still glowing in radio light long after the dust has settled. Or maybe there's something entirely new, something we haven't modeled yet, something our instruments are only just now catching. A new kind of cosmic structure. That's the beauty and frustration of the invisible universe. Sometimes it gives us shapes without explanations, and we're left to wonder what drew them. So far, only a few dozen ORCs have been found, but more powerful surveys are coming, more eyes on the sky, and perhaps soon we'll know what they really are, or perhaps not, because the cosmos doesn't always answer back. Time feels steady, seconds tick, days pass. But that's only because you're far from anything extreme. Get close to a black hole, and time itself begins to stretch. This isn't science fiction. It's a prediction of Einstein's general relativity, confirmed by observation. The stronger the gravitational field, the slower time runs, at least as seen by someone farther away. So if you hovered near the event horizon of a black hole, not inside it, but just above that invisible boundary, your seconds would become hours to someone watching from afar. To you, everything would feel normal. Your heart beats, your thoughts flow. But when you return, if you could, you'd find that years had passed elsewhere. This is called gravitational time dilation. The closer you are to the mass, the more space-time curves, and black holes curve it to the extreme. On Earth, the effect is tiny. Time ticks just a bit faster on mountaintops than at sea level, measurable only with atomic clocks. But near a stellar black hole, the difference becomes profound. Near a supermassive black hole, like the one at the center of the Milky Way, it becomes surreal. In theory, you could experience minutes while centuries passed outside. This idea inspired the film Interstellar, where 1 hour on a distant planet near a black hole cost the characters 7 years back home. And though dramatized, the math behind it is surprisingly solid. But it raises deeper questions. What does it mean that time isn't fixed? That it bends and stretches depending on where you are? Could advanced civilizations use this effect? Could they hide in slow time near black holes, letting the rest of the universe race ahead? Or could time dilation be used for deep space hibernation, letting travelers endure centuries without feeling them? We don't know yet, but the fact that time is not universal, that it depends on gravity, changes everything. Time isn't just a river, it's a fabric, warped by weight, shaped by mass. And near a black hole, the future flows at a different speed. You've seen ripples on a pond. Now imagine ripples in space itself. That's what gravitational waves are, disturbances in the very fabric of the universe. First predicted by Albert Einstein in 1916 and finally detected 100 years later in 2015. But what causes them? Only the most violent events in the cosmos. When massive objects, like black holes or neutron stars collide, they don't just send out light, they send out waves of gravity, spreading at the speed of light in all directions. These waves stretch and squeeze space as they pass, but don't expect to feel them. By the time they reach Earth, gravitational waves are incredibly faint. So faint they change distances by less than the width of a proton. Detecting them requires instruments of astonishing precision like LIGO in the United States and Virgo in Europe. These observatories use laser interferometry, splitting a beam of light into two paths, bouncing them off mirrors kilometers apart, and measuring tiny differences in how they return. When a gravitational wave passes, the arms of the instrument stretch and shrink by impossibly small amounts, and we hear the echo of a distant cataclysm. The first confirmed detection in 2015 came from the merger of two black holes more than 1 billion light years away. And yet, their collision briefly released more energy than all the stars in the observable universe in the form of gravitational waves. Since then, we've heard dozens of events, black holes spiraling into each other, neutron stars merging in brilliant flashes, even hybrid collisions, dense star with black hole. Each one tells a story light can't, because gravitational waves pass through matter undisturbed. They let us see deep inside dense, dark events that would otherwise be hidden. And the future, projects like LISA, a space-based gravitational observatory, aim to detect even lower frequency waves. These could reveal the mergers of supermassive black holes, the vibrations of the early universe, or even exotic objects we haven't imagined. We are no longer just looking at the sky, we are listening to it. And in those whispers of stretched space, the universe speaks a language older than light. They're everywhere, flowing through your body, through the earth, through the walls. Right now, trillions of them are passing through you, unnoticed. They don't glow. They don't stop. They don't care. These are neutrinos, often called ghost particles. They were first proposed in the 1930s to explain missing energy in radioactive decay. For decades, they were theoretical phantoms, but slowly we learned they were real, and not just real, but vital to understanding how the universe works. Neutrinos are created in enormous numbers during nuclear reactions, like those in the sun, exploding stars, and particle accelerators. But what makes them strange is how little they interact with matter. A neutrino could pass through a light year of lead and not touch a single atom. That makes them hard to detect, but not impossible. Deep underground, inside facilities like Super Kamiokande in Japan or Ice Cube in Antarctica, scientists watch for the rare moments when a neutrino does interact, usually producing a tiny flash of light. These detectors are buried under mountains or ice to shield them from other types of radiation. They are silent, patient observatories. And what do they find? Neutrinos from the sun arriving 8 minutes after being born in fusion. Neutrinos from distant supernovas created when massive stars collapse, and even high-energy neutrinos from outside the galaxy, perhaps born in the hearts of black holes or the jets of active galaxies. Each one is a message from a violent place. And because neutrinos move at nearly the speed of light and are barely affected by matter, they can escape places that light cannot. We've detected neutrinos from SN 1987A, a supernova that lit up a nearby galaxy. And every such detection teaches us more about what lies inside these cataclysmic events. But there are mysteries too. Neutrinos come in 3 flavors, and they seem to change between them as they travel, something that wasn't supposed to be possible. This oscillation implies they have mass, though it's unimaginably small. That small mass might add up. Some scientists believe that neutrinos, billions of them per cubic meter, might play a role in the universe's missing mass. Not dark matter exactly, but a shadow of it. They're quiet, they're invisible, but when we learn to listen, ghost particles can tell stories that light never could. It sounds ominous, like something from science fiction, the zone of avoidance, but it's real, and it hides a part of the universe from our eyes. The zone of avoidance is a region of the night sky where we can't see, not because of distance, but because of our own galaxy. The Milky Way, seen from Earth, is a glowing band of stars. It's beautiful, but it also blocks our view. That band is full of gas, dust, and stars stretching across the entire sky. And in certain directions, it becomes so dense that telescopes can't see past it. That's the zone of avoidance. Roughly 10 to 20% of the sky is obscured this way. And it's a problem because that portion might contain major structures, clusters of galaxies, dark matter concentrations, or even massive gravitational anomalies that tug at other galaxies across the universe. One such mystery is the Great Attractor, a region pulling hundreds of thousands of galaxies toward it, including our own. We know it's there because of its gravitational influence, but it sits in or behind the zone of avoidance. So what's causing that pull? A massive cluster? A giant filament of matter? Or something else entirely? We're still not sure because we can't see clearly, but astronomers have found ways to peek behind the curtain. Infrared telescopes can pierce through dust better than visible light instruments. Radio surveys can trace galaxies by their hydrogen emissions. X-ray observatories can catch signals from energetic sources like galaxy clusters or quasars hiding behind the Milky Way's veil. And with each new method, the zone shrinks just a little. In recent years, astronomers have discovered several hidden galaxies behind the Milky Way. Some are massive, some are oddly shaped, some are part of previously unknown clusters. But the zone still exists, still hiding, still whispering that maybe, just maybe, something bigger lies behind it. It's humbling. In a universe filled with telescopes, satellites, and surveys, there are still places we can't quite reach, and maybe that's part of the mystery. That even now, the cosmos keeps some secrets to itself. The universe has a memory, and we can see it. It's called the cosmic microwave background, or CMB, a faint glow that fills the sky in every direction. It's not light from stars or galaxies. It's the leftover radiation from the Big Bang itself. This ancient afterglow dates back nearly 13.8 billion years, when the universe was just 380,000 years old. At that time, space cooled enough for atoms to form, allowing light to travel freely for the first time. That light is still traveling, stretched into microwaves by the expansion of space, and it's almost perfectly uniform. Almost. Because in 2004, astronomers noticed something odd. A region in the CMB that's colder than it should be, larger than any typical fluctuation, and far more empty than expected. They called it the cold spot. It spans about 5 degrees on the sky, a massive patch when you consider the full dome above us, and it's about 70 microkelvin colder than the average temperature of the CMB. That might not sound like much, but on cosmic scales, it's huge. So what caused it? One explanation is a supervoid, a vast region of space with fewer galaxies, fewer clusters, less matter overall. If light from the early universe passed through such a void, it would lose energy, arriving slightly colder. But the void doesn't fully explain the depth of the cold spot. And some argue it's too large to be just a statistical fluke. So, what else? One idea, controversial but intriguing, is that the cold spot might be a bruise, a mark left from when our universe collided with another in a kind of multiverse scenario. A universe bumping into ours during the inflationary phase, distorting the cosmic background. Is that science fiction? Maybe, but it's consistent with some inflationary models, and it reminds us how much we don't know about the beginning. The cold spot remains one of the most puzzling features in modern cosmology. Not bright, not loud, just colder. A quiet anomaly in a sea of warmth. As if the universe is keeping one corner of its memory, frozen in time. Where are we? It's not an easy question in cosmic terms, because galaxies don't just float in isolation, they belong to something larger. The Milky Way is part of a group of galaxies called the local group. That group is part of a cluster, and that cluster, it flows into something even greater. In 2014, scientists gave it a name, Laniakea. It means immense heaven in Hawaiian, and it is. The Laniakea supercluster is an enormous structure, more than 500 million light years across. It contains over 100,000 galaxies, all interconnected by gravity and motion. The Milky Way is just one thread in its vast tapestry. But Laniakea wasn't discovered by counting galaxies. It was found by watching them move. Astronomers measured the peculiar velocities of thousands of galaxies, not just how fast they're moving away due to cosmic expansion, but how they drift towards certain regions. These motions revealed hidden gravitational basins, places where matter collects and pulls other matter in. By mapping those flows, scientists traced the contours of a cosmic watershed, and Laniakea was the result. A basin of attraction centered near the mysterious Great Attractor. Everything inside Laniakea flows inward, drawn by the gravity of this massive region. That's how it's defined, not by where galaxies are, but by where they're going. And it's beautiful. The structure resembles a vast filament with strands branching out like a living network. Between those strands lie cosmic voids, vast empty regions with almost no galaxies at all. Together, they form what we now call the cosmic web. Our solar system orbits a star in a spiral arm of the Milky Way. The Milky Way is in the local group. The local group is in the Virgo cluster, and the Virgo cluster is in Laniakea. We are, quite literally, part of an immense heaven. But Laniakea is not the whole story. Beyond its borders lie other superclusters, and all of them, together, drift through space, perhaps toward another great attractor, perhaps just expanding with the fabric of the universe. It humbles us to realize that our galaxy is a speck in a cluster, inside a stream of galaxies, inside a structure so vast we only just learned its name. Black holes usually come from stars. Massive stars burn bright, collapse, and leave behind darkness. But what if some black holes are older than stars themselves? That's the idea behind primordial black holes, mysterious objects that might have formed in the first moments after the Big Bang. In those early fractions of a second, the universe was hot, dense, and wildly unstable. Quantum fluctuations rippled through the infant cosmos, and in rare spots, those fluctuations may have concentrated enough mass in tiny volumes of space to collapse into black holes, no stars required. These black holes wouldn't be large. Many would be microscopic, but some might be massive enough to survive to this day, quietly floating through space, nearly impossible to detect. And yet, they might explain some of our biggest cosmic mysteries. Take dark matter, the invisible substance that outweighs all the visible stars and galaxies combined. We don't know what dark matter is, but some scientists have proposed that primordial black holes might make up a fraction or even all of it. They would be dark, massive, and gravitationally active, perfect candidates in theory. But are they real? So far, we've never directly seen a primordial black hole, but experiments like microlensing surveys, which look for brief brightening of stars when a black hole passes in front of them, have placed limits. Too many such black holes would cause effects we'd already notice. Still, certain masses remain possible, and recently, observations from LIGO and Virgo gravitational wave detectors have revealed black hole mergers involving objects of unusual sizes. Some of these mergers don't match what we expect from stellar collapse. Could they be ancient? Could they be primordial? It remains an open question. But if even a handful of primordial black holes exist, they would be the oldest stable structures in the universe, survivors from a time before light, before atoms, before structure, tiny relics of chaos, time capsules of the very beginning. They remind us that not all darkness comes from death. Some comes from birth, the violent, invisible birth of the universe itself. Imagine a world where the sky is always on fire, not just red, not just bright, but searing. A place where the horizon glows with a permanent sunrise and the atmosphere is being stripped away grain by grain like sand in a storm. That world exists, and it's being eaten alive. This is a type of planet known as a hot Jupiter, a gas giant orbiting so close to its star that its atmosphere is boiling off into space. It orbits once every Earth day or less, locked in a death spiral around its host. The heat is unbearable, thousands of degrees, and the gravity from the nearby star tugs relentlessly at its gaseous envelope. Astronomers first discovered such doomed planets when they noticed faint trails of material bleeding off into space. These planets are literally forming a tail, not unlike a comet, as their atmospheres are pulled into long, glowing streams by the star's radiation. Over time, this process will strip them bare. Some might be reduced to rocky cores. Others may disappear entirely. This phenomenon tells us a lot about how stars and planets interact over time. It challenges old models of planetary stability and migration. Why would a gas giant ever form so close to a star? The current theory is that they don't. They migrate inward, pulled by gravitational tugs over millions of years, until they reach a point of no return. And here's the haunting part. We've caught some of them right in the act. Using telescopes like Hubble and TESS, scientists have observed atmospheric loss in real time, spectral fingerprints showing hydrogen, helium, and heavier elements trailing behind these burning worlds like smoke behind a torch. One of the most studied cases of this is a planet that loses the equivalent of billions of tons of gas per second. It's like watching a planet dissolve. We don't yet know how long such a planet can survive, but we do know this. It offers a window into one of the most dramatic ends a world can face, not by collision, not by freezing, but by slow, fiery disintegration, death by starlight. Far beyond our solar system, in the direction of the constellation Leo, there's a small, faint red star known as K218. It's the kind of star you'd likely overlook in a telescope, quiet, cool, and unassuming. But orbiting this dim sun is a planet that has captured the attention of astronomers around the world. Its name is K218b, and it might be wet. Not with rivers or lakes or polar caps like we see on Mars, but with something far more profound, an atmosphere filled with water vapor, and beneath that possibly an entire ocean wrapped in hydrogen and mystery. Discovered in 2015, K218b didn't initially stand out. It's larger than Earth, about 2.5 times its size, and nearly 9 times as massive. Too big to be a rocky world like ours, but too small to be a full gas giant like Neptune. It exists in a middle category of exoplanets, a sub-Neptune, a kind of world we have no direct equivalent for in our own system. But what changed everything was what came next. In 2019, scientists pointed the Hubble Space Telescope toward K218b and detected something no one had seen before, the spectral signature of water vapor in its atmosphere. And more than that, it was located within its star's habitable zone, that fragile ring of space where the temperatures could allow liquid water to exist. That single discovery instantly elevated the planet from just another data point to something closer to a dream. Then, in 2023, the James Webb Space Telescope followed up. What it saw was astonishing. In addition to water, the planet's skies appeared to contain methane and carbon dioxide, molecules that together raised a tantalizing possibility that the atmosphere might be chemically imbalanced in a way that, on Earth, is associated with life. Scientists call this a biosignature candidate. It's not proof, not even close, but it's enough to whisper a question that's haunted us for centuries. Could something be living out there? If K218b is what some researchers suspect, a Hycean world, short for hydrogen-rich and ocean-covered, it would be a planet with an immense liquid sea beneath thick clouds where the pressure and chemistry are nothing like Earth. But high above that ocean, in the upper atmosphere, temperatures and conditions might be just right. Warm, stable, watery. A place, perhaps, where tiny life forms could float freely, feeding on chemical nutrients and drifting through alien clouds. We don't know what lies beneath those veils of gas. We can't see the surface, if there even is one. But in K218b, we see a mirror held up to possibility. A reminder that Earth-like life might not need Earth-like conditions. That habitability isn't a narrow corridor, but a wide and wild frontier. And maybe, just maybe, there are other skies, red and dim, filled with vapor, where something is watching back, or simply existing quietly as it always has. Picture a world where mountains shimmer not with snow, but with the gleam of crystal, where the bedrock isn't granite or basalt, but something far rarer, compressed, hardened carbon. Deep beneath a molten surface, time and pressure have forged something almost unthinkable, a landscape of diamond. This is the haunting idea behind carbon planets, exotic worlds that may form in star systems rich in carbon but poor in oxygen. In our own solar system, Earth was born from a cloud where oxygen dominated, giving us a world built from silicates and water. But change the recipe, tip the balance, and chemistry begins to write a different story. In theory, a carbon-rich disk around a young star could give rise to a planet where graphite replaces granite, where carbides line the crust, and where, in the crushing heat of the deep interior, diamonds grow not as rare gemstones, but as geological layers, vast, cold, and eternal. We may have already found a candidate. Orbiting the star 55 Cancri, just 40 light-years away, is a world called 55 Cancri e, a planet so hot it glows with infrared light, its surface likely molten. It's twice the size of Earth, but nearly 8 times as massive, suggesting a dense, compact core. Early models hinted at an interior layered with carbon, enough perhaps to form diamond under immense pressure. And though newer measurements have complicated that picture, the idea has lingered, not because we've confirmed it, but because the physics makes it possible. What would such a world look like? You wouldn't walk its surface. Temperatures likely exceed 2,000 degrees Celsius. Volcanic activity might be constant, the crust in flux, rivers of glowing liquid carbon oozing through fractures. The skies could be dark with soot and carbon-rich gases, thick with heat and fury. But buried deep, past the fire, past the fractures, miles down, lies a possibility. Diamond, forged not in beauty salons or deep mines, but by the planet itself, through eons of weight and time. The very idea bends our imagination. On Earth, diamonds are rare treasures, symbols of wealth and permanence. But in a universe where carbon is plentiful and pressure is relentless, they might be mundane, the planetary equivalent of granite. It's a humbling shift in perspective. And yet, it's more than geology. Carbon planets remind us that alien doesn't always mean unfamiliar in form. Sometimes it means familiar things used in wildly unfamiliar ways. The elements we know, carbon, iron, silicon, can build cathedrals we've never seen, mountains that shine, cores that crackle with unimaginable strength, continents that glint under alien suns. We may never set foot on such a place, but with each strange signal, each odd density reading from distant stars, we add another fragment to the map of what's possible and what might be waiting, glittering in the dark. High above the scorched horizon of an alien world, the winds howl at 2,000 miles per hour. They scream across a dark sky filled with shimmering vapor, twisting through superheated clouds of silicate particles. And then, as if conjured by some infernal storm, shards of glass begin to fall, sideways. This is not science fiction. This is a real planet, and what it endures defies even our wildest visions of hell. It's known in scientific circles as a type of ultra-hot Jupiter, a gas giant orbiting so close to its star that its dayside temperature can climb above 1,800 degrees Celsius. That's hot enough to vaporize metal and melt rock into gas. The atmosphere is not just hot, it's a forge, a place where elements are stripped, recombined, and hurled across the sky in storms more violent than anything Earth has ever seen. One of the most famous examples is a planet orbiting a star slightly smaller than our Sun, only a few million kilometers away. On this world, the extreme heat on the star-facing side creates a stark imbalance. Silicate particles, essentially the ingredients of sand and glass, are lifted into the atmosphere where they condense into droplets high in the sky. But on the night side, where the temperature drops, not to cold, but to merely less unbearable, these droplets cool and harden, forming tiny, sharp crystals of glass. Then come the winds. Supersonic jet streams rip through the atmosphere, driving the glass shards sideways at breakneck speeds. These aren't gentle drizzles or peaceful flakes. This is horizontal rain made of cutting edges, a storm that would shred metal, let alone any fragile probe we might dream of sending there. The planet is tidally locked, meaning one side always faces the star while the other lies in endless night. That contrast between relentless fire and muted darkness fuels the planetary chaos. It's a system in constant imbalance, with energy perpetually surging from one hemisphere to the other. And still, through this madness, we learn. By studying the way starlight filters through the atmosphere of such planets, telescopes like Hubble and James Webb can detect the fingerprints of silicates and metals, revealing the composition of clouds that should not exist in weather that shouldn't be possible. In doing so, we stretch the limits of planetary science. We redefine what an atmosphere can be. We watch the very sky turn to glass. These worlds are not habitable. They are not friendly, but they are extraordinary. They remind us that the universe is not built for comfort. It's built for extremes. And somewhere out there, beyond our gentle blue earth, lie planets where the air itself cuts like a blade, and the rain falls like shattered mirrors from a sky on fire. In the quiet dawn of a distant world, two shadows stretch across the ground, not because of tall mountains or giant moons, but because overhead there are two suns rising in tandem, one bright and yellow, the other smaller and redder, climbing the sky side by side. It's not a scene from science fiction, it's real, and it's stranger than anything Star Wars ever imagined. For decades, astronomers wondered whether planets could even exist in binary star systems, places where the gravitational pull of two suns might tear any world apart or fling it out of orbit entirely. The math seemed messy, the models unpredictable, but in 2011, all that changed. That's when NASA's Kepler mission confirmed the first planet orbiting a pair of stars. Since then, we've found many more, and now we know planets can, in fact, orbit two suns, not just survive there, but thrive. These are called circumbinary planets, and their orbits are unlike anything we know in our own solar system. Instead of tracing a path around a single anchor point, they move in elegant loops around a constantly shifting center of gravity. The stars themselves dance in a tight orbit, and the planet moves around them both, gracefully navigating a cosmic ballet of light and motion. The most famous of these is Kepler 16b, a gas giant roughly the size of Saturn. If you stood on a solid surface there, though it's likely a gas world with no such terrain, you would see two suns rise and set in intricate patterns, sometimes together, sometimes apart. Some days might last weeks. Some shadows would twist in ways our minds can barely picture. But these aren't just novelties. Circumbinary planets open a new frontier in the search for life. Because if rocky planets can exist in stable orbits around two suns, and there's no reason to think they can't, then the number of potentially habitable worlds in the galaxy could be far greater than we once believed. The double sunlight might lead to extreme seasons, complex climate patterns, and beautiful alien skies. Plants, if they ever evolved there, might have to adapt to two wavelengths of light. Nights might be shorter, or far, far longer. We once imagined such worlds as fantasy. Now they are data points, measurements, spectra, real. And they remind us that the architecture of star systems isn't fixed, it's playful. The universe is more creative than we gave it credit for. And somewhere out there, under twin suns, a planet spins in quiet balance, proving that even the most cinematic dreams can turn out to be true. Imagine standing on the edge of an alien world where the sky is never clear, where no sunlight ever fully breaks through, and every horizon fades into a dense, endless mist. The air is thick, the colors muted, the surface, if it even exists, hidden beneath layers of vapor. This is a planet wrapped in mystery, not because we haven't looked, but because we can't see through its fog. Astronomers call it a sub-Neptune, a planet larger than Earth but smaller than Uranus, cloaked in an atmosphere so dense and opaque that light struggles to escape. One of the most intriguing examples we've found is a world that defies our best instruments. Even under the gaze of the James Webb Space Telescope, its atmospheric signature remains stubbornly featureless, as if the planet itself is choosing to keep its secrets. This kind of planetary enigma challenges everything we thought we knew about exoplanets. When light from a host star passes through a planet's atmosphere during a transit, we expect to see absorption lines, chemical fingerprints that reveal what the air is made of. But for this world, those lines are flat, silent, as though the planet wears a veil we can't pierce. What causes this? The leading theory is that its atmosphere is filled with haze, thick layers of photochemical smog created by complex reactions between sunlight and atmospheric molecules. On Earth, we see this in polluted cities. On Titan, Saturn's largest moon, it's a permanent golden-orange cloak. But here, the haze might be even more extreme, muting all signals, absorbing all clues. Some researchers think this fog hides a deep ocean beneath, a vast liquid layer, perhaps hundreds of kilometers thick, resting on a solid core we'll never glimpse. Others suggest a dense, hydrogen-helium envelope, masking a more exotic interior. Whatever the truth is, we only know one thing for sure. This planet refuses to show its face, and in that refusal, it becomes all the more fascinating. We're used to thinking of exploration as a process of revelation, of stripping away mystery. But some planets remind us that mystery can be part of the story, that even with the best tools, some places will always resist easy answers. In a universe full of dramatic extremes, lava worlds, glass storms, frozen giants, sometimes the strangest place of all is the one that hides in silence, shrouded in fog, offering no reflection and no reply. Picture a planet where there are no continents, no islands, no dry land at all, just water, stretching in every direction, as far as the eye could see. No coastlines, no mountain ranges, only an unbroken ocean, hundreds of kilometers deep, cloaked in clouds and bathed in faint starlight. This is the vision of a true ocean world, a planet where liquid water doesn't just fill lakes and seas, but covers the entire surface in a global, all-encompassing flood. In our solar system, we have icy moons like Europa and Enceladus, which may have oceans beneath layers of ice. But a fully aquatic exoplanet with no land masses and no frozen crust takes this idea to another scale. Scientists believe such planets could be common across the galaxy, formed beyond the snowlines of their star systems, then migrating inward, carrying with them vast stores of water. One candidate lies about 100 light years away. Its size and mass suggest a density too low for rock, too high for gas, pointing instead to a composition dominated by water. Not just surface water, but layer after layer. A high-pressure ocean above, a deeper, denser layer below, and possibly even exotic forms of ice locked in place by crushing internal forces. This isn't the water we know. It's water reshaped by alien gravity and heat, forming structures and states of matter we've never encountered firsthand. On such a planet, sunlight might filter through the upper atmosphere into a pale, clouded ocean. Beneath the surface, it would grow dark quickly. Pressure would build with impossible speed. At a depth of 100 kilometers, the water might begin to compress into forms of ice that are solid not because of cold, but because of pressure. These so-called Ice 7 or Ice 10 layers might form the base of the ocean, a strange, crystalline seafloor above a hidden core. Would life be possible here? Perhaps, but only in a narrow zone, a twilight layer near the top where light and chemistry interact. Microbial life, if it ever took hold, could float freely in the upper reaches, drawing energy from the faint rays of a distant sun. Deeper down, warmth from the core might drive hydrothermal vents, as they do in Earth's oceans, potentially sparking even more complex ecosystems in total darkness. We often imagine life needing land, needing stability, but Earth's oceans are a reminder that life began in the water, not on the shore. And if planets like these are as common as we suspect, the galaxy may be filled with liquid worlds, vast, silent, and teeming with possibilities beneath their endless waves. To them, land is the alien concept, and silence, not shorelines, is home. Some planets live too fast. They're born, drift inward, and spiral so close to their stars that they barely survive. Their days are short, their skies a furnace, their fates already written. These are the hell planets, worlds that orbit so close to their stars, they're constantly on the edge of vaporizing. We've found many of them. They complete an orbit in mere hours or a few Earth days, circling their stars at distances so small they'd fit well inside Mercury's path. From that proximity, the heat is relentless. Temperatures soar to thousands of degrees Celsius, hot enough to melt iron, vaporize rock, and strip atmospheres away molecule by molecule. Their surfaces, if they have any, are likely seas of molten minerals. Lava flows may stretch for thousands of kilometers. Clouds, if they exist at all, could be made of vaporized metals or silicates, forming strange mineral mists under the blaze of permanent daylight. And on some of these worlds, the heat is not the only threat. The stars they cling to often blast them with powerful radiation and stellar wind, tearing at their atmospheres and exposing their cores. In extreme cases, the planets begin to evaporate, not just lose gas, but physically shrink, like a stone boiling away under a blowtorch. These planets come in different sizes and types. Some are rocky, Earth-like in mass but utterly scorched. Lava planets, baked dry and glowing with thermal energy. Others are gas giants, pulled so close to their stars that their outer layers swell up and begin to drift off into space. Some may even leave behind nothing but a rocky remnant, the skeletal remains of what was once a giant. The existence of these hellish orbits challenges our models of planetary formation. Most planets likely form farther out, where things are cooler and calmer. So how did these worlds get so close? The answer lies in migration, gravitational interactions, sometimes with other planets, sometimes with the disk of gas and dust they formed in, that slowly drag them inward over millions of years. It's a slow death, but a spectacular one. In some systems, we've caught planets in the act of decaying, their orbits tightening year by year. Eventually, some may fall into their stars entirely, consumed in a final burst of radiation, their mass returned to the fire that once gave them form. We call them hell planets, because it's the only language we have for such extremes. But for all their violence, they're part of the universe's quiet math, a reminder that not all systems are stable and not all worlds are meant to last. Some are born to burn. At first glance, it looks like a star with a faint blur beside it, an optical smudge, a trick of light. But as astronomers looked closer, they realized what they were seeing wasn't an illusion. It was a planet, and it had a tail, like a comet. In some distant systems, planets orbiting perilously close to their stars are shedding material so rapidly that it streams out behind them, forming long, delicate trails of gas and dust. These aren't icy comets from the outer reaches of a solar system. They're rocky worlds, or even gas giants, melting and evaporating in real time. These tails are made of silicate particles, hydrogen, helium, or heavier elements, depending on the planet's composition. The intense radiation from the nearby star heats the atmosphere or surface to extreme temperatures, lifting particles upward until they're caught in the stellar wind and blown away. One of the most striking cases is a planet smaller than Mercury, orbiting its star in less than a day. It's so close that its surface likely reaches 2,000 degrees Celsius, hot enough to boil rock. That rock vapor then expands into space, creating a dusty tail that trails behind the planet like smoke. Observations suggest this world may be losing hundreds of thousands of tons of mass every second. Eventually, these planets may disappear altogether, whittled down to nothing by the very star they orbit. What we're witnessing, in a sense, is planetary erosion on a cosmic scale, not over geological epochs, but over mere millions or even thousands of years. The shape of the tail can also reveal surprising details. Some curve dramatically, tracing arcs behind the planet's orbit like a painter's stroke. Others flicker and pulse, expanding and contracting in rhythm with solar activity. They're not just passive trails, they're dynamic, sculpted by magnetic fields, stellar winds, and orbital speed. These comet-like planets are more than astronomical curiosities. They challenge our assumptions about planetary lifespans, about the line between planet and debris. They blur the boundaries of what a planet can be, and in doing so, they offer something rare, a glimpse of destruction as it happens, a fleeting chapter in a planet's life caught in the act of vanishing. Imagine a world where one side never sees darkness and the other never sees light. A place where the sun hangs frozen in the sky, motionless, searing one hemisphere with eternal day while the other lies in unbroken frozen night. This is not a poetic metaphor. It is a real and common outcome of physics, the natural state of many exoplanets across the galaxy. These are the tidally locked worlds. Just like our moon always shows the same face to Earth, many exoplanets orbiting close to their stars become gravitationally locked, always turning the same side toward their sun. For planets orbiting small, dim stars like red dwarfs, which emit less light and require habitable planets to orbit much closer, tidal locking is almost inevitable. At first glance, that seems like a deal breaker for life. One side scorched, the other frozen. How could anything survive? But the reality is more nuanced and far more fascinating. In the blistering daylight zone, temperatures can soar high enough to vaporize water and cook rock. The sky would be brilliant, the ground parched, the atmosphere swirling with heat. On the night side, everything freezes. Oceans, air, even carbon dioxide. A desert of ice and silence. But between these two extremes, along the Terminator line, the thin band where night meets day, something astonishing might happen. There, temperatures could be moderate. Winds could circulate heat from the day side to the night side, softening the harsh contrast. Giant planetary jet streams might howl around the globe, distributing energy and maintaining dynamic weather systems. In that twilight belt, under a dim orange or red sun permanently fixed near the horizon, conditions could become stable and even habitable. Some models suggest that cloud cover on the day side could reflect enough heat to keep it from boiling over, while greenhouse gases on the night side could trap warmth and prevent total freeze-out. It's a planetary balancing act, precarious but possible. Tidally locked planets also offer strange views. The sun would never rise or set. In the middle of the day side, it would shine directly overhead forever. On the terminator, it would hover on the horizon, casting long, permanent shadows. And on the dark side, eternal night, broken only by starlight and auroras. These worlds remind us that habitability doesn't always mean Earth-like. Life, if it exists, could evolve in narrow ribbons of twilight, feeding on gradients of heat and light, adapted to rhythms unlike anything we know. Plants might always face one direction. Winds might shape entire ecosystems. Civilizations, if they ever arise, might be born in the Shadowlands, where fire and frost meet in delicate equilibrium. In the grand diversity of planets, tidally locked worlds are no outliers. They are expected, common, maybe even the rule rather than the exception. And if so, the story of life in the universe might be a story not of sunshine, but of shadows. Drifting alone through the galaxy, surrounded by endless dark, there are planets that orbit nothing. No sun rises to warm them. No star lights their sky. They move silently through interstellar space, cold, invisible, and utterly free. These are rogue planets, and they may outnumber the stars themselves. Unlike most planets, which form and remain within the gravitational pull of a parent star, rogue planets are castaways. Some were likely born in star systems, but were later ejected, flung into the void by chaotic interactions with other planets or passing stars. Others may have formed alone in the darkness, born from collapsing clouds of gas that never ignited into stars. However they came to be, the result is the same: a planet with no sun. What does that mean for the surface of such a world? Without sunlight, temperatures would plummet to unimaginable lows. The surface would be frozen solid, the atmosphere, if one existed, locked down in layers of ice. But inside, things could be very different. Even without a star, a rogue planet might still have internal heat, left over from its formation or generated by the decay of radioactive elements. If it has a thick enough atmosphere or an insulating ice shell, that heat could be trapped, maintaining a warm interior. And if there's water buried beneath the surface, it might stay liquid, not in oceans under open skies, but in hidden pockets beneath kilometers of ice, a subsurface sea in total darkness. In fact, some scientists believe rogue planets could harbor conditions suitable for life, protected by rock, pressure, and geothermal warmth. Life that never sees light. Life that evolves not in cycles of day and night, but in endless twilight. Rogue planets are hard to find. Without the glow of a nearby star, they don't reflect or block light in the ways we typically detect exoplanets. But their gravity still acts, and in rare moments, when one passes in front of a distant star, it can bend the starlight just enough to be seen through a phenomenon called gravitational microlensing. So far, we've detected only a few, but models suggest there could be billions in our galaxy alone. Silent travelers, cold refugees, planets that drift between the stars like forgotten worlds, each carrying its own story, its own chemistry, its own version of isolation. In the cosmic balance between light and dark, these are the wanderers, lost, unbound, and hauntingly real. And if life can survive there, then the universe is even more resilient than we imagined. At first glance, it doesn't make sense. You measure the mass of a planet, it's not especially heavy, maybe a bit more than Jupiter. But then you look at its size, and it's enormous, bloated, swollen, far larger than physics says it should be. The numbers don't line up. The planet seems too light for its volume, too airy for its appearance. These are the inflated planets, gas giants with mysteriously puffed up atmospheres that make them appear much larger than they ought to be. Some of them are so large they rival small stars in diameter, yet their mass remains modest. They're low-density giants with atmospheres that have expanded outward like cosmic balloons. Scientists have struggled to explain them because under standard planetary models, gas giants should compress under their own gravity. Their size should be tightly related to their mass. But inflated planets break that rule. So what's going on? The leading suspect is heat, not from within the planet, but from its star. Most inflated planets orbit extremely close to their host stars, where intense radiation constantly bombards their atmospheres. The energy heats the upper layers, causing them to expand like air in a hot air balloon. These planets can be tidally locked, with one side always facing the star, leading to extreme temperature gradients and powerful winds that circulate heat around the globe. But heat alone may not be enough. Some models suggest additional mechanisms, like ohmic heating, where charged particles in the planet's atmosphere create electrical currents as they move through magnetic fields, generating extra heat that seeps down into the planet's depths. Others propose tidal heating, caused by the gravitational pull of nearby moons or the star itself, constantly kneading the planet like dough. Whatever the cause, the result is the same: a planet with a giant bloated radius, often with less than half the density of water. You could theoretically take one of these worlds and drop it in an ocean, and it would float. Inflated planets are fragile. Their atmospheres are weakly bound and often leak into space, especially if the planet orbits too close to its star. Some may be caught in a slow process of evaporation, losing mass over time, drifting toward a fate similar to that of comet-like planets with tails. Yet for all their instability, they offer a glimpse into planetary diversity. They show us that mass alone doesn't define a world, that size, structure, and environment are equally powerful sculptors. They also force us to rethink what a gas giant is. Not all are dense and compact like Jupiter. Some are swollen and strange, brief balloons in the long life of a solar system, stretching their skies until the pressure breaks and they collapse, shrink, or disappear. They are planets in flux, and that makes them one of the most vivid examples of how alien the universe can be, even when it's made from the same ingredients we know. Every so often, the universe delivers a quiet contradiction, something that simply shouldn't be there. A planet that breaks the rules, a world that, by every simulation and theory we've built, shouldn't have formed, and yet does. These are the impossible planets, exoplanets, that defy the models we use to understand how planetary systems are born and evolve. One of the clearest examples is a gas giant found extremely close to a small, dim star, a kind of planet that shouldn't have been able to form in the meager disk of gas and dust such a star can offer. According to classical formation theory, there simply isn't enough material that close to the star to create something so massive. And yet, there it is, orbiting every few days, bloated and burning. In other cases, we've discovered super-Earths with ultra-short orbital periods, circling their stars in less than a day, often so close they skim the stellar surface. These planets should have spiraled into their stars long ago, consumed by gravity or radiation. Their presence suggests either that they're newly arrived, or that something is missing from our understanding of orbital decay. There are planets in binary systems where the gravitational dynamics are so unstable we never expected long-term orbits to persist, yet some of these worlds have circled their twin suns for billions of years, in calm, graceful loops. There are even planets orbiting white dwarfs, the burned-out remnants of dead stars. These systems should have been annihilated during the star's death throes, and yet somehow planets remain or reassemble. One of the most puzzling findings is the existence of planets with strange combinations of mass and radius, too dense for their size or too large for their mass. Some may have massive cores wrapped in only thin layers of gas. Others might be hollow-seeming giants, bloated beyond explanation. These outliers challenge the very way we infer internal structure from external measurements. The fact that we keep finding these anomalies tells us something important. Our models are incomplete. They work well for many systems, including our own, but the galaxy is vast, and nature plays by no fixed script. Sometimes planets form in chaotic environments. Sometimes they migrate in strange ways, encountering and surviving events that should have destroyed them. And sometimes they teach us that what we believed was impossible simply wasn't imaginative enough. Every new impossible planet adds a brushstroke to the cosmic portrait we're trying to paint. Each one is a challenge and an invitation to look again, think differently, and accept that in a universe of hundreds of billions of stars, the exceptions may be as common as the rules. We rarely see them, but they shape everything. Magnetic fields are the invisible scaffolding of planetary life, shielding atmospheres, deflecting solar wind, and stabilizing climates. On Earth, our magnetic field protects us from cosmic radiation, guides compasses, and dances across the poles in glowing auroras. But what about alien worlds? Do they have magnetic fields too? And what would those look like? The answer, slowly emerging from data and theory, is yes. Some exoplanets likely have magnetic fields, and in some cases, they might be even stronger or stranger than our own. The generation of a magnetic field depends on a planet's interior. It needs a conductive fluid, like molten iron or metallic hydrogen, in motion. On Earth, that fluid is in the outer core. For gas giants like Jupiter, it's a massive layer of metallic hydrogen swirling under intense pressure. The rotation of the planet turns this internal motion into a global magnetic shield. Some exoplanets, particularly massive gas giants orbiting close to their stars, are expected to have powerful magnetic fields. In fact, they may need them, because the closer a planet is to its star, the more it's bombarded by stellar wind, streams of charged particles that can strip away atmospheres over time. Without a magnetic field, many close-orbiting planets might be left bare, dry, or vaporized. Interestingly, we've begun to detect signs of exoplanetary magnetism, not directly, but through radio emissions and the behavior of surrounding plasma. In one case, astronomers observed a strange bending in the stellar wind as it passed by a planet, suggesting the presence of a magnetic bubble, a magnetosphere large enough to carve space around the world like Earth's does. There are even hints that magnetic fields could affect habitability. A planet in the habitable zone with liquid water and a stable orbit might still be uninhabitable if it lacks a magnetic field, because over time it would lose its atmosphere and be exposed to lethal radiation. Conversely, a planet slightly outside the Goldilocks zone might remain viable if its magnetic field traps heat and protects the surface. Magnetic fields also lead to one of the most beautiful phenomena we know, auroras. On alien worlds, These could be far more intense than on Earth, glowing not just at the poles, but perhaps across entire hemispheres, ignited by powerful stellar flares. Red dwarfs, in particular, are known for violent outbursts. A strong magnetic field might mean the difference between destruction and spectacle. We don't yet know how common these fields are, but as our instruments improve, we're beginning to glimpse the invisible architecture of distant planets, not just their size, orbit, or composition, but their force fields, their shields, their silent defenses. And in a universe full of harsh radiation, collapsing stars, and high-energy storms, that invisible shield may be one of the most important features a planet can have. Not just for science, but for survival. When we imagine life beyond Earth, we tend to picture planets, rocky worlds in the habitable zone, bathed in the glow of a steady sun. But nature doesn't always follow that script. Sometimes, the most promising places for life don't orbit stars at all. They orbit planets. These are the exomoons, and some of them might be even more promising than the worlds they circle. We know that moons in our own solar system already hint at habitability. Europa, Enceladus, and Titan, all moons of gas giants, show signs of subsurface oceans, organic chemistry, or thick atmospheres. If these features can arise here in our quiet corner of the galaxy, there's every reason to believe they can arise elsewhere, and perhaps more dramatically. The key lies in energy. A moon orbiting a massive planet can be kept warm, not by sunlight, but by tidal forces. The gravity of the host planet stretches and compresses the moon's interior, creating frictional heat, enough to melt ice, sustain subsurface oceans, and drive volcanic activity. It's a constant internal engine, powered by gravity rather than light. Now imagine that same mechanism applied to a larger moon, one Earth-sized perhaps, orbiting a giant exoplanet in the habitable zone of its star. There, the moon receives both stellar light and planetary tidal heating, a double source of warmth. Add a protective magnetic field, possibly shared with the planet itself, and you have a compelling recipe for life. Astronomers are actively searching for these worlds. The first strong candidate, a potential Neptune-sized moon, was detected in 2017, orbiting a Jupiter-like exoplanet. Though its nature is still debated, the discovery opened the door to a new frontier, that moons could outnumber habitable planets and in some cases outperform them. And moons offer other advantages. Their tidal cycles could stir oceans and nutrient flows. Their skies might hold double eclipses, one from the planet, another from distant stars. Their surfaces might glow with reflected light, their nights lit not by moonlight, but planet light, the soft, colorful glow of their host looming large in the sky. In science fiction, we've imagined places like Pandora from Avatar, lush moons with exotic ecosystems suspended above giant gas worlds. But science is beginning to catch up. We now understand that these environments are not just plausible, they might be common. And while we haven't confirmed a habitable moon yet, each new discovery brings us closer, not just to new types of planets, but to a whole new class of worlds, not planets, not stars, but something in between, something orbiting in the shadows of giants, quietly collecting heat, chemistry, and time. Maybe the first alien life we find won't come from a planet at all. Maybe it will come from a moon, listening, waiting, circling in silence. If life exists beyond Earth, how would we recognize it? We might never see its oceans or forests or creatures directly, but we might see its breath. That's the idea behind biosignatures, chemical traces in a planet's atmosphere that hint at biological activity. On Earth, life has transformed the air, oxygen, methane, carbon dioxide, ozone, all in unusual balance, shaped not by geology or chemistry alone, but by living processes. And if life is doing the same on distant worlds, we might be able to detect it from across the stars. For years, this was a theoretical hope, but now, with the arrival of telescopes like James Webb, that hope has become a target. The key is transit spectroscopy. When a planet passes in front of its star, a small fraction of starlight filters through its atmosphere. That light carries information, tiny absorption lines like fingerprints that tell us what gases are present. It's delicate work, requiring extraordinary sensitivity, but it has already begun to bear fruit. One of the most promising discoveries so far is on K2-18b, a planet in the habitable zone of a red dwarf star. The James Webb Space Telescope detected water vapor, carbon dioxide, and hints of methane, a mix that on Earth could point toward life. Though the signals aren't conclusive and non-biological explanations exist, it's the first real detection of multiple potential biosignature gases in a planet's atmosphere. Another target is TRAPPIST-1e, one of 7 rocky planets orbiting a nearby ultra-cool dwarf star. While definitive biosignatures haven't been found yet, the TRAPPIST system is ideal for study. The planets are small, temperate, and close enough for detailed observations. As more data comes in, we may soon be able to rule out or confirm atmospheres and search for imbalances that hint at something more. Scientists are especially interested in non-equilibrium chemistry, gas combinations that shouldn't exist together unless something is constantly replenishing them. On Earth, the coexistence of methane and oxygen is a classic example. Methane should quickly break down in an oxygen-rich atmosphere. The only reason it stays is because life keeps producing it. But there's caution too. False positives are a real risk. Volcanoes can emit methane. Stellar radiation can split water and create oxygen. Planets with unusual surfaces or compositions might mimic biosignatures without any biology at all. That's why context is everything. Planetary mass, temperature, orbit, stellar activity, all must be considered to understand what we're really seeing. The hunt for atmospheric biosignatures is just beginning. Each detection is a puzzle, and we are learning to read the chemical poetry of distant skies. The tools are improving, the targets are growing, and somewhere out there, perhaps, a planet is quietly exhaling, not into a void, but into a telescope's waiting eye. And in that breath, we might one day hear the first whisper of a living world. We've come a long way since the first exoplanet discovery in the 1990s. Today, we've cataloged thousands. We've found hot Jupiters, super Earths, lava worlds, and ocean planets. We've glimpsed atmospheres, measured chemical fingerprints, and imagined alien weather. But one goal still hovers just out of reach: the dream of finding a true Earth twin. A small, rocky planet in the habitable zone, with an atmosphere we can study in detail. A planet where life could exist, or already does. To reach that next level, we'll need new eyes on the sky, and the most promising among them are two ambitious missions, LUVOIR and HABEX. LUVOIR, the Large UVs Opticals or IR Surveyor, is a concept for a massive space telescope, possibly with a mirror up to 15 meters wide, dwarfing even the James Webb. It would be capable of imaging Earth-like planets directly, not just as transits across stars, but as tiny points of reflected light. LUVOIR could analyze dozens, even hundreds, of potentially habitable exoplanets, breaking their light into spectra and searching for biosignatures, surface oceans, cloud cover, and more. Where James Webb sees the shadows of planets passing in front of stars, LUVOIR could see the planets themselves, orbiting beside the star like pale blue dots in miniature. And with its powerful instruments, it could observe in multiple wavelengths, from ultraviolet to near infrared, opening a far broader window into atmospheric chemistry. HABEX, or the Habitable Exoplanet Observatory, is a smaller but more focused mission. Its primary goal is direct imaging of Earth-like worlds around Sun-like stars. HABEX plans to use a unique technology called a star shade, a giant, flower-shaped shield that would fly tens of thousands of kilometers ahead of the telescope, blocking out a star's light while letting the dim glow of nearby planets shine through. It's a simple idea with enormous implications, turning the blinding light of a star into manageable darkness so the planets around it can emerge. Both LUVOIR and HABEX aim to answer one of the most profound questions in science. How common is life in the universe? But they also offer something deeper, the ability to study alien worlds as worlds, not just as data points. to map their weather, seasons, and maybe even surface colors, to detect how their atmospheres change over time, to begin building not just a catalog of planets, but a geography of the galaxy. These missions are still in the proposal and planning stages. They represent the next generation, the instruments that could launch in the 2030s or beyond. But they are more than dreams. They are blueprints, and if funded and built, they could change everything. Because if life is out there, it may not be sending signals. It may not build civilizations or spacecraft. It may simply breathe and let its light scatter into space. And we, with LUVOIR or HABEX, may finally be able to see it. For every exoplanet we've found, there are countless more we haven't. Most of the galaxy remains uncharted, trillions of worlds orbiting hundreds of billions of stars, each shaped by its own collisions, chemistry, and chaos. And somewhere out there are planets so bizarre, so unexpected, that they lie beyond anything we've yet imagined. The strangest worlds may not be the ones we know, but the ones still waiting to be seen. We've already been surprised many times. Planets that rain molten glass, worlds lit by two suns, gas giants puffed up like balloons, and lava planets spinning in permanent daylight. None of these were predicted before we found them. They were discovered first, explained later. So what's next? What kinds of planets might be out there, just beyond the reach of our telescopes? Some scientists speculate about mirror worlds, planets with the same mass and orbit as Earth, but with wildly different chemistry. Imagine a planet where life evolved using silicon instead of carbon, where oceans are made of methane or ammonia or even supercritical fluids, where clouds float above seas of exotic liquids under thick, colored skies. Others imagine dark planets, worlds so coated in light-absorbing material that they reflect almost nothing, rendering them nearly invisible. These might be hot Jupiters wrapped in soot-like compounds, appearing as tiny dips in starlight or flickers of heat against the cosmic background. We may have already missed some, simply because they're too dark to detect. Then there are the hypothetical crystal planets, worlds formed almost entirely from a single mineral under pressure, like sapphire or diamond. Or plasma planets, so close to their stars that their atmospheres are partially ionized, glowing with ghostly auroras that wrap the entire planet like a shroud. And some possibilities are even stranger. Worlds that orbit black holes lit by distorted starlight from distant suns, or planets that exist in trinary systems, tugged in complex figure eights by three competing stars, or rogue planets with bioluminescent life glowing faintly in the endless dark, never touched by daylight. As telescopes grow stronger and data deepens, we'll start to catch glimpses. A strange wobble in a star's movement, a spectral signature that doesn't make sense, a flicker of light that fades too fast. And when we do, we'll remember that our understanding of planets is still young. Earth, Mars, Jupiter, these are just local examples. The universe is experimenting far more widely. It's building worlds we haven't dared to name yet. The strangest worlds are still out there, waiting in silence. And one day, they will surprise us all over again. We're used to thinking of planets as layered things, a crust, a mantle, and deep at the center, a dense core that holds it all together. Even in the case of gas giants like Jupiter or Saturn, most models assume there's something solid at the heart, a rocky or metallic core hidden beneath countless layers of hydrogen and helium. But what if that's not always true? What if some gas giants have no core at all? This idea isn't just theoretical. It's been seriously considered as astronomers study the internal structures of gas giants both in our solar system and beyond. Some exoplanets we've observed appear to have such low density, so puffed up and diffuse, that they challenge the standard model of planetary formation. Their mass is spread out over enormous volumes, with no clear sign of a heavy center. How is that possible? The prevailing explanation lies in formation and fate. Most planets begin with a solid seed, a core of rock and metal that gathers gas around it. But in the chaos of a forming system, collisions and heating can disrupt that structure. In some cases, the intense pressure and temperature deep inside the planet might cause the core to dissolve into the surrounding fluid envelope, vanishing not by explosion, but by chemical blending. In other cases, a gas giant might form directly from a collapsing cloud of gas, skipping the solid phase entirely. This kind of gravitational collapse, similar to how stars form, could lead to a planet that is gas all the way down. No rocky heart, no molten center, just hydrogen and helium, slowly growing denser as you descend, but never becoming truly solid. The implications are huge. A planet with no core would behave differently in terms of magnetism, internal heat, and atmospheric chemistry. It might lack a strong magnetic field. Its winds could be deeper and more chaotic. Its response to tidal forces from nearby moons or stars could be less stable. In other words, it wouldn't just be strange on the inside, it would act strange on the outside too. And because we can't dig into these planets directly, we rely on light, on spectroscopy, gravity measurements, thermal readings, and the subtle way a planet wobbles as it moves. It's detective work on a cosmic scale, and the clues keep pointing to the same unsettling possibility, that not all planets have hearts. Some may be endless, a sky that deepens into cloud, that deepens into pressure, that deepens into darkness, with nothing waiting at the center, but more of the same. In a way, it makes them feel less like planets and more like storms without end. Giants, yes, but hollow, filled with motion, but not with solidity, with presence, but not with anchor. And yet, in their emptiness, they remain majestic, a reminder that in the universe, not everything that looks massive is built on something strong. Some things are vast simply by expanding and never stopping. There are places in the lava planet's universe where the ground is not solid, where the very surface of a planet is in a constant state of eruption, glowing, seething, moving like water. These are where oceans are made not of water, but of molten stone, and the landscape is a living, burning tide. We've discovered several candidates for such worlds, most of them orbiting extremely close to their stars, so close that one side, the star-facing hemisphere, becomes a literal magma sea, heated beyond the melting point of rock, while the night side remains cooler but still hostile. These planets are often tidally locked, with the same face always turned toward the star, creating a permanent inferno on one half and a strange, sullen twilight on the other. One such world is thought to have lava tides, waves of molten rock that shift as the planet's gravitational and thermal stresses deform its surface. Winds made of vaporized minerals blow across the sky, cooling into clouds that might condense as stone rain. The air itself could carry sodium and silicon, the atmosphere not a gas in the traditional sense, but a plume of vaporized crust. It sounds like science fiction, but it's all grounded in hard data, spectral readings from space telescopes that pick up the chemical fingerprints of vaporized rock, thermal maps that show extreme temperature gradients across the planet's surface, and orbital patterns that match the predictions for heat-blasted, close-in orbits. The formation of these worlds is just as fascinating as their appearance. Lava planets likely begin as terrestrial, rocky bodies, not unlike Earth, but over time, the gravity of their parent stars pulls them inward. As they migrate closer, their surfaces begin to melt. The very skin of the planet liquefies. Mountains become waves. Craters become whirlpools of fire. And beneath that molten crust, possibly an iron core, struggling to hold the planet together under immense thermal strain. Volcanoes might erupt endlessly. The planet may never cool. It may never rest. Some models suggest that the lava might circulate, rising on the hot side, flowing toward the dark side, then cooling and sinking in a kind of rock cycle not seen on Earth. This circulation could maintain active geology for billions of years, long after the planet should have gone silent. That the lava planets are inhospitable, violent, and dazzling, laboratories of planetary extremes. They show us what happens when matter is pushed to its limit, when the idea of land becomes fluid, when the concept of a horizon flickers in waves of liquid fire. In a universe filled with water worlds, gas giants, and frozen moons, lava planets are a reminder that not all heat gives life. Some of it simply burns forever. In the quiet vastness of space, a single point of light begins to grow. First, it brightens gently, then suddenly, violently, it explodes into brilliance. For a few brief weeks, it can outshine an entire galaxy. Then, just as quickly, it fades. But what's left behind can shape the universe. This is a supernova, the death of a massive star, and one of the most powerful events the cosmos can produce. It is destruction on a scale almost beyond comprehension. Yet in that destruction, something miraculous happens. Creation. Stars are nuclear furnaces. In their cores, hydrogen fuses into helium, then into heavier and heavier elements: carbon, oxygen, silicon. But even the most massive stars can only go so far. When they begin fusing iron, the process stalls. Iron doesn't release energy when fused, it consumes it. And without the outward pressure of fusion to counteract gravity, the star collapses under its own immense weight. In a matter of seconds, the core crushes down. The outer layers fall inward and then rebound outward in a catastrophic blast, a supernova. The explosion sends shock waves rippling through space, flinging star matter across light years. This blast creates new elements: gold, silver, uranium, forged in the unimaginable pressure and heat. Everything heavier than iron in your body, in our planet, in every ring and circuit was born this way. The calcium in your bones, the iodine in your blood, the gold in your wedding ring, all made in the heart of a dying star. But the story doesn't end with debris. What's left behind may be even stranger. Sometimes, the collapsed core becomes a neutron star, a city-sized object more massive than the sun, with gravity so strong it warps space around it. In rarer cases, the collapse continues until even neutrons can't hold back gravity, and a black hole is born. Supernovae are rare in any single galaxy, but across the universe, they happen constantly, and their impact is enormous. They can trigger new star formation by compressing nearby clouds of gas. They can sterilize nearby planets with radiation. They can shape the arms of galaxies. They can be seen from billions of light years away. In the cosmos, not all endings are quiet. Some end in fire, light, and transformation. And from that final moment, new worlds begin. There are moments in the universe so violent, so sudden, that they release more energy in a few seconds than our sun will emit in its entire lifetime. These are gamma ray bursts, the brightest, most extreme explosions we have ever detected, and they arrive without warning. They come from far-off galaxies, often billions of light years away. For just a few seconds, a flash of high-energy radiation erupts, invisible to human eyes, but blinding to our instruments. When the first ones were discovered in the late 1960s, during military satellite missions meant to monitor nuclear tests, no one knew what they were. The flashes came from deep space, fast, bright, and terrifyingly powerful. We now believe there are two main types of gamma ray bursts. The first are long-duration bursts, lasting several seconds to a few minutes. These are thought to come from the death of massive stars, specifically when a dying star's core collapses into a black hole and the twin jets of matter are fired from the poles at near light speed. If one of those jets happens to be pointed toward Earth, we witness a gamma ray burst. The second type, short duration bursts, last less than 2 seconds and are believed to be caused by the merger of two neutron stars, a collision so dense and energetic that it creates both gravitational waves and intense bursts of gamma radiation. Either way, the result is the same: a flash of energy that can fry electronics on satellites, distort the Earth's ionosphere, and leave scientists scrambling to understand the aftermath. We've even asked the question, could a gamma ray burst end life on Earth? It's not just science fiction. If one occurred close enough, within a few thousand light years, and was directed at us, the radiation could strip away our ozone layer, exposing the surface to harmful ultraviolet light and triggering a global extinction event. Some researchers even speculate that ancient gamma ray bursts may have played a role in past mass extinctions. But they're also signals, cosmic sirens announcing the formation of black holes, the collisions of stellar remnants, and the limits of energy release in nature. They allow us to peer into the early universe, since many of the most distant ones come from the first generations of stars. Gamma ray bursts are not just powerful, they are precise, focused beams of annihilation, narrow, fast, and final. And every time one appears, we are reminded how fragile light and life truly is. We tend to think of planets as stable, permanent things, solid ground, predictable orbits, steady rotations. But in the history of the cosmos, planetary collisions are not rare events, they're foundational ones. Planets are not born peacefully. They are built in fire, shattered by violence, and shaped again and again by impact. Early in a star system's life, chaos rules. Dozens, even hundreds, of protoplanets spiral through unstable orbits, colliding, merging, or tearing each other apart. Gravity pulls them together, but when their paths cross, the result is often cataclysmic. Imagine two planetary bodies, each the size of Earth or Mars, colliding at tens of kilometers per second. The force released is trillions of nuclear bombs, enough to melt crusts, vaporize atmospheres, and fling entire mountains into orbit. The result isn't just destruction, it's reformation. Astronomers now believe that many of the planets we observe, including those in our own solar system, bear the scars of ancient collisions. Mercury's oversized iron core may be the result of a massive impact that stripped away its outer layers. Uranus is tipped on its side, possibly due to a glancing planetary blow. And Earth may owe its very identity to one. We'll return to that specific collision in the next chapter. But planetary smash-ups happen elsewhere too, and sometimes we witness them indirectly. In distant star systems, telescopes like Kepler and TESS have caught glimpses of fresh debris disks, warm clouds of dust that suddenly appear around young stars. Those may be the aftermath of planetary collisions, a signal that two worlds just crashed into one another, their fragments now glowing in infrared light as they cool. Some systems even show pulses of strange light or unusual chemical signatures, suggesting molten surfaces, ejected cores, or atmosphere-stripping impacts. These are not just theoretical. They're observable consequences of a chaotic process that still echoes across the galaxy. Collisions can also explain planetary oddities, extreme orbits, tilted axes, missing atmospheres. They're a reminder that planets are not sculpted gently. They're hammered into being, one crash at a time. And even after billions of years, it never fully stops. In a dynamic universe, peace is temporary, but from every collision, something new is forged. Look up at the moon, and you're seeing the aftermath of a cataclysm. A world torn apart, a planet changed forever, because our moon, quiet, familiar, serene, was born in fire. And it may have been the result of the most important impact in Earth's history. The leading theory, known as the giant impact hypothesis, suggests that early Earth didn't always have a moon. In the turbulent youth of the solar system, Earth was still forming, young, molten, and frequently bombarded. Then one day, a Mars-sized object, a rogue protoplanet we call Theia, struck Earth at a glancing angle. It wasn't a head-on crash. It was worse. A slow-motion, planet-shattering blow. The force was enough to vaporize vast sections of Earth's outer layers and completely destroy Theia. The impact ejected an enormous plume of molten rock and metal into orbit, forming a glowing ring of debris. Over time, maybe months, maybe years, that ring coalesced into the moon. But the consequences didn't stop there. That impact likely tilted Earth's axis, giving us seasons. It may have accelerated Earth's rotation, shortening our days, and most importantly, the newly formed moon began to stabilize Earth's wobble, preventing wild climate swings and chaotic precession. Without the moon, Earth's climate might have fluctuated too violently for life to ever gain a foothold. Chemical analysis of lunar rocks supports this origin story. The moon's composition is almost identical to Earth's outer layers, suggesting a shared origin, but with key differences that imply extreme heat and mixing. No other theory explains those observations as clearly as a massive collision. And Theia, it's gone, merged with Earth, scattered into space, or perhaps lingering deep within our planet. Some scientists even speculate that unusual structures near Earth's core, dense, continent-sized blobs, could be remnants of Theia's mantle still buried inside us after 4 billion years. It's poetic in a way. The moon that lights our night sky may be the ghost of a lost world, the still glowing memory of the day Earth became what it is. From destruction came balance, from chaos came orbit, and from one terrible impact came home. In July 1994, something extraordinary happened, something we had never seen before. For the first time in human history, we watched as a celestial body collided with a planet in real time. The object was a comet. The target was Jupiter, and the impact left scars big enough to swallow Earth whole. The comet was called Shoemaker-Levy 9, a fragile traveler that had been captured by Jupiter's immense gravity years earlier. Instead of escaping, it entered a decaying orbit, one that pulled it closer and closer until the tidal forces of Jupiter's gravitational field tore it apart. The result was a string of icy fragments, lined up like pearls in space, each tens of kilometers wide. Astronomers around the world turned their telescopes toward Jupiter, uncertain of what would happen next. Then, one by one, the fragments began to strike. Over the course of several days, they slammed into Jupiter's upper atmosphere at more than 200,000 kilometers per hour, releasing energy equivalent to millions of nuclear bombs. The impacts sent plumes of gas rising 3,000 kilometers above the cloud tops and left dark scars, bruise-like blemishes, visible even in amateur telescopes. But beyond the spectacle, Shoemaker-Levy 9 reminded us of something more profound. Jupiter protects us. Because of its massive size and powerful gravity, Jupiter acts as a kind of cosmic vacuum cleaner, sweeping up comets, asteroids, and space debris that might otherwise strike the inner planets, including Earth. In many simulations of solar system dynamics, Jupiter is the great deflector, pulling dangerous objects away or catching them in its own atmosphere. Without Jupiter, Earth might have suffered many more catastrophic impacts over its history. Some scientists refer to Jupiter as a gravitational shield, though it's not perfect. Its presence increases the complexity of object trajectories and sometimes even sends objects inward. But overall, the gas giant plays a vital role in reducing the number of high-speed intruders that reach our neighborhood. Shoemaker-Levy 9 was a rare event, but it served as a warning and a gift. It showed us that planetary impacts are still happening, even now. It reminded us how fragile our planet truly is, and it revealed that in the darkness of space, we are not entirely alone. Sometimes the giants take the hit for us. 66 million years ago, Earth was full of life. Dinosaurs roamed vast continents, flying reptiles soared through the skies, and lush forests stretched across the land. Then, in a moment, just one terrible instant, everything changed. A rock, roughly 10 kilometers wide, slammed into what is now the Yucatan Peninsula in Mexico. It struck with the force of more than 1 billion nuclear bombs, traveling faster than a bullet, and released more energy than all the world's volcanoes could produce in 1 million years. This was the Chicxulub impact, one of the most devastating events in Earth's history and the most famous mass extinction trigger ever discovered. The immediate effects were apocalyptic. The impact blasted a crater more than 150 kilometers wide and over 20 kilometers deep. Rock vaporized. Oceans boiled. Firestorms swept across continents. Earthquakes circled the globe. And worse still, the collision hurled billions of tons of sulfur, ash, and debris into the atmosphere, blotting out the sun. What followed was not just fire, it was darkness. Temperatures plummeted. Photosynthesis stopped. Plants died. Then the animals that fed on them. An estimated 75% of all life on Earth vanished, including every non-avian dinosaur. But from that extinction came transformation. The disappearance of the dominant species opened evolutionary paths that had been blocked for millions of years. Small mammals, once insignificant in the shadow of giants, began to diversify. Among them were the ancestors of primates, and eventually of us. The evidence for this story is now overwhelming. The iridium layer found in rocks all over the world, an element rare on Earth but common in asteroids. The Chicxulub crater, still visible beneath layers of sediment. The fossil record, showing a sudden global collapse of ecosystems at the end of the Cretaceous. And so, the sky that brought death also brought renewal. The Chicxulub impact is a reminder of Earth's vulnerability and its resilience, that in a single moment the course of life can shift, and that every living thing today, in some way, carries the legacy of that ancient fire. The age of dinosaurs ended not with a whimper, but with a flash, and in the ashes, the age of humans began. Not all cosmic catastrophes come from the sky. Some rise from deep within the earth in events just as devastating, just as transformative, but slower, darker, and longer lasting. One such event occurred around 74,000 years ago in what is now Sumatra, Indonesia. It was the eruption of a supervolcano called Toba, and it may have nearly wiped us out. The Toba supereruption is believed to be the largest volcanic eruption on Earth in the last 2 million years. It expelled an estimated 2,800 cubic kilometers of material, blanketing parts of Southeast Asia in ash and launching aerosols high into the stratosphere. That ash fell as far as India and East Africa. The explosion was thousands of times more powerful than any eruption in recorded history, a VEI8 event, the highest possible on the Volcanic Explosivity Index. But the ash cloud was only part of the disaster. Far more dangerous was what followed: a volcanic winter. As fine ash and sulfur dioxide spread across the planet, they blocked sunlight, cooled global temperatures, and disrupted rainfall patterns. Some models suggest that Earth's average temperature may have dropped by as much as 3 to 5 degrees Celsius, with even greater local declines. Crops didn't fail. They hadn't been invented yet, but ecosystems did. Plants withered, animal populations crashed, and with them, early human communities. Genetic evidence hints at something chilling. Studies of mitochondrial DNA suggest that modern humans passed through an extreme population bottleneck around this time. Possibly as few as a few thousand individuals survived globally. We don't know for certain that Toba caused this, but the timing aligns. It's possible that our entire species was nearly erased, not by asteroid or war, but by a volcano half a world away. And yet, we survived. The bottleneck may have shaped the genetic diversity of modern humans. Some researchers suggest it fostered closer cooperation, migration, and innovation. In the millennia following Toba, humans spread rapidly across Africa and beyond. Whether driven by hardship or opportunity, the species endured and grew. Toba reminds us that extinction isn't always sudden. Sometimes it comes as a slow, cold shadow that lingers for years. And survival doesn't always roar. Sometimes it whispers. In that whisper, humanity found its voice. The sun, for all its warmth and constancy, hides a violent heart. Beneath its golden surface, magnetic fields twist and snap like cosmic whips, releasing titanic eruptions of energy and charged particles into space. Most of the time, these outbursts pass unnoticed, but sometimes they hit Earth, and when they do, the sky lights up and our fragile technology trembles. The most powerful such event ever recorded happened in 1859. It's known today as the Carrington event, named after British astronomer Richard Carrington, who was observing the sun that day when he saw something strange, a sudden blinding flash of light from a sunspot. What we now know was a solar flare, the visible start of a coronal mass ejection. Just 17 hours later, and incredibly fast transit times, the storm hit Earth. What followed was unprecedented. The night skies erupted in auroras, so bright they were seen as far south as the Caribbean. In the northern United States, people could read newspapers at midnight by the shimmering green and red glow. Telegraph systems, the cutting-edge technology of the time, failed spectacularly. Sparks flew from telegraph machines. Operators were shocked, and some systems continued to send messages even after being disconnected from their power sources. This was not just a beautiful light show. It was a planet-wide electrical event. If a storm of this magnitude were to happen today, the results would be far more devastating. Power grids could collapse, satellites could be fried, GPS, internet, and communication networks could be crippled. Flights, navigation, banking systems, all of modern life would be vulnerable, and the risk is not theoretical. In 1989, a solar storm far weaker than the Carrington event knocked out the power grid in Quebec, plunging millions into darkness. In 2012, Earth narrowly missed a Carrington-class storm. A massive CME erupted from the sun and passed through Earth's orbital path, but Earth had just moved on. Scientists monitor the sun constantly now. Spacecraft like SOHO and the Parker Solar Probe track solar activity, giving us hours, sometimes days, of warning, but we can't stop it. We can only brace. The Carrington event was a reminder that our star is not tame. It giveth warmth, light, energy, but it also threatens. And someday, perhaps soon, the sky may flare again, not with beauty, but with warning. From the deepest reaches of space, invisible messengers arrive, tiny high-energy particles traveling at nearly the speed of light. They pass silently through magnetic fields, slice through planetary atmospheres, and sometimes strike us directly. These are cosmic rays, and though they are smaller than atoms, their impact can be enormous, even written into our DNA. Cosmic rays are mostly protons, fragments of atoms accelerated to incredible energies by powerful events, supernovae, active galactic nuclei, and possibly even more exotic sources like colliding black holes. They don't come in steady streams, but in bursts and waves, shaped by solar activity and the motion of our solar system through the galaxy. Most are harmless. Earth's magnetic field and atmosphere protect us, shielding the surface from the highest doses. But a small fraction gets through. They interact with the atoms in our atmosphere, triggering particle showers, cascades of secondary particles that rain down, some reaching the ground and even our cells. And sometimes these particles hit DNA. One impact can break chemical bonds, alter a sequence, or flip a genetic switch. Most of the time, our cells repair the damage, but occasionally, a cosmic ray triggers a mutation, a tiny random change that becomes part of the genetic code. Some mutations are neutral, some are harmful, but some, by chance, are useful. This is one of the quietest, strangest truths about cosmic evolution. Mutation drives change, and cosmic radiation is one of the engines behind it. Over millions of years, cosmic rays may have contributed to the rise of new traits, the fall of old ones, and the gradual transformation of species. They are not the only cause of mutation, but they are a cosmic contributor to Earth's biology, constantly delivering randomness into the delicate balance of life. And during periods of intense stellar activity, like when a nearby star explodes in a supernova, the dose can rise. Some researchers believe past extinction events or bursts of evolutionary change may have been influenced by increased cosmic radiation, disrupting ecosystems and accelerating mutation rates. For astronauts beyond Earth's protective shield, the risk is even greater. Cosmic rays can damage tissue, increase cancer risk, and pose a major challenge to deep space missions. But here on Earth, they continue to fall, unseen, unfelt, and constant. Cosmic static, tapping on the glass of our biology. Tiny accidents, seeded from the stars, and within those accidents, evolution. Most stars die quietly, some go out in brilliant explosions, but a few, the most extreme, the most exotic, do something else entirely. They shake, not like a tremble or a ripple, but a deep internal fracture that sends energy roaring across the galaxy. These are starquakes, and they happen on some of the strangest objects in the universe, magnetars. A magnetar is a type of neutron star, the collapsed core of a massive star that died in a supernova. It's only about 20 kilometers across, the size of a city, but it can weigh more than our sun. Its gravity is so intense that atoms are crushed, its crust is ultra-dense, and the whole star is wrapped in a magnetic field a quadrillion times stronger than Earth's. It's that magnetic field that sets a magnetar apart. Twisting, snapping, constantly shifting under pressure, it distorts the surface of the star until, one day, the crust gives way. And when that happens, a starquake erupts. The energy released can be enormous. In one case, detected in 2004 from a magnetar called SGR 1806-20, a burst of gamma rays reached Earth from 50,000 light-years away, and for a fraction of a second, it outshone the entire Milky Way. Satellites in orbit were overwhelmed. Earth's upper atmosphere expanded under the sudden wave of energy, and yet the magnetar barely flinched. A starquake is caused when the immense magnetic forces inside the magnetar twist and shear its rigid crust, not unlike tectonic plates on Earth, but on a cosmic scale. The crust shifts just a few centimeters, and the result is the energy equivalent of 10 to the power of 39 ergs. That's more than our sun will emit in 100,000 years, released in a fraction of a second. These bursts aren't just destructive, they're also informative. They allow us to study the interiors of neutron stars, probe the limits of matter, and even test the laws of physics under conditions we could never reproduce on Earth. Magnetars don't last long in cosmic terms, just tens of thousands of years. But in that brief lifetime, they unleash some of the most violent events in the universe. They are not explosions. They are not collisions. They are something rarer. A star breaking itself from the inside out. And in that fracture, the cosmos listens. In late 2019, something strange happened in the sky. Betelgeuse, the red supergiant that blazes bright in the shoulder of Orion, began to fade, not a little, a lot. Over just a few weeks, it dimmed by more than 60%, visibly changing one of the most familiar constellations in the night sky. For a moment, the astronomical world held its breath. Was this the beginning of the end? Was Betelgeuse one of the largest, most unstable stars we can see, about to explode in a supernova? It wasn't, at least not yet. But the event, now known as the Great Dimming, was a powerful reminder of how close and how volatile some stellar catastrophes truly are. Betelgeuse is enormous. If placed in the center of our solar system, it would stretch beyond the orbit of Jupiter. It's nearing the end of its life, fusing heavier elements in its core and preparing eventually for collapse. That much we've long known. But what we hadn't seen until 2019 was just how dramatically its outer layers could shift in real time. At first, the dimming was a mystery. Telescopes around the world focused in, and multiple theories emerged. One suggested a massive star spot, a cool patch on the surface that temporarily reduced the brightness. Another pointed to a sudden ejection of material, a belch of gas and dust from the star's outer layers that cooled and condensed into a giant dust cloud, blocking our view from Earth. Eventually, the dust explanation gained the most support. Images from the Very Large Telescope in Chile even showed changes in Betelgeuse's shape, a visible distortion caused by the asymmetrical outflow of matter. In other words, the star had coughed. And that cough taught us something. It showed that stars don't just fade in the abstract span of eons. Sometimes they change before our eyes. Betelgeuse is expected to go supernova within the next 100,000 years, a blink in cosmic time. When it does, it will briefly become as bright as the full moon and be visible in daylight. but no one knows when. The Great Dimming was not the final act, but perhaps a rehearsal, a warning flicker from a star nearing the end of its script. And now, every night it rises, we wonder, is tonight the night Betelgeuse goes dark forever? In the vast cold clouds between the stars, places we call nebulae, the seeds of suns are waiting. These star-forming regions are quiet to the eye, but not to the universe. Inside them, gravity works slowly and patiently, pulling gas and dust together until something ignites. And once a single star is born, it can set off a chain reaction, turning a silent cloud into a cosmic factory of fire. It begins with a collapse. Somewhere in the molecular cloud, a pocket of gas grows dense enough to trigger gravitational infall. As it shrinks, it heats up. A protostar is born. And when fusion finally begins, when hydrogen becomes helium in its core, the star erupts with energy and light. But its birth doesn't just end the story of its own formation. It changes the entire neighborhood. Young, massive stars in particular, O and B-type stars, emit intense radiation and powerful stellar winds. They blow bubbles into the surrounding cloud, pushing gas away, carving out cavities. These winds compress the edges of nearby clumps of gas, triggering new collapses, new stars, and new outbursts. It's a feedback loop, a fire that spreads. In some cases, a massive star dies quickly in a supernova, and the explosion slams into the nearby cloud, triggering even more star formation. The shock wave acts like a hammer, compressing matter into filaments and cores. This cascading process is how entire clusters of stars are born, not one at a time, but in waves, one birth igniting the next. Astronomers have observed these phenomena in regions like the Orion Nebula, the Carina Nebula, and NGC 346. These glowing clouds teem with infant stars, some still wrapped in disks of material, forming planets. In infrared and radio wavelengths, we can see the signature of the collapse, the outflows, the heat, the whole cycle in motion. And sometimes, a single massive star, just one, can change everything. Its presence accelerates or halts star formation across light years. It can sculpt a region for millions of years, creating beauty and violence in equal measure. Star factories are not gentle nurseries. They are shaped by interstellar cause and effect, by pressure and fire, by the fragile balance between collapse and destruction. And in the chaos, suns are born, not alone, but together, in a galactic chain reaction that will light the sky for ages to come. Not all stars stay where they're born. Some are ejected, hurled from the centers of galaxies, flung across the void at breakneck speeds, cast out by forces so immense that they escape not just their stellar neighborhoods, but sometimes their entire galaxy. These are hypervelocity stars, and they are the fastest rogue travelers in the universe. First predicted in theory, then discovered in the early 2000s, hypervelocity stars are real and rare. While most stars orbit calmly within the gravitational pull of their galaxy, a hypervelocity star breaks free, traveling at speeds of hundreds or even thousands of kilometers per second. Some move so fast they exceed the escape velocity of the Milky Way, destined to wander intergalactic space for eternity. But what could fling something as massive as a star? One of the most likely mechanisms involves a close encounter with a supermassive black hole. Imagine a binary star system, two stars orbiting one another, drifting too close to the monster lurking at the center of the galaxy. As the pair nears the black hole, tidal forces tear them apart. One star is captured, spiraling inward toward the black hole, and the other is catapulted outward, its orbit converted into a slingshot of unimaginable speed. This gravitational three-body interaction is like a cosmic billiards game, with the black hole breaking the pair and launching one ball into deep space. But that's not the only path to hypervelocity. Some stars may be flung outward during galactic collisions, such as the future merger between the Milky Way and Andromeda. Others could be ejected from dense stellar clusters or by the collapse of massive systems where gravitational instability turns chaos into acceleration. Observations have found hypervelocity stars moving away from the galactic center and even from the Large Magellanic Cloud, suggesting multiple origins. Some of these stars are massive and young, burning bright and hot, destined to live short, fast lives far from where they began. They carry more than just speed. They carry stories of violence, of disruption, of cosmic dynamics writ large. They show us that even stars, those great anchors of the night sky, can be dislodged and flung like sparks from a galactic forge. And somewhere out there, in the silence between galaxies, those sparks are still flying. Some stars are born together, twin lights orbiting each other in an elegant gravitational dance. These binary systems are common in the universe, and for much of their lives, the stars coexist peacefully, orbiting a shared center of mass. But sometimes the balance breaks. One star begins to swell or collapse or steal, and what begins as a partnership becomes a slow-motion catastrophe, a death spiral. This deadly dance can take many forms, but the most dramatic begin when the stars grow old. As one star exhausts its nuclear fuel, it expands into a red giant, spilling its outer layers into space. If its companion is close enough, it begins to accrete that matter, pulling it in with its gravity, gaining mass and spinning faster. A stream of gas flows from one star to the other, forming a glowing accretion disk, often lighting up in X-rays and ultraviolet. The system becomes unstable. If the receiving star is a white dwarf and it gains too much material too quickly, the pressure can ignite runaway fusion on its surface, triggering a nova. Or if the mass exceeds a critical limit, the entire white dwarf can detonate in a Type Ia supernova, obliterating itself and potentially its partner. In other cases, both stars may be compact remnants, two white dwarfs, or two neutron stars, or even black holes. Over millions or billions of years, they lose energy by radiating gravitational waves, spiraling closer and closer until finally they collide. The final seconds are explosive. Two neutron stars merging can create a kilonova, a flash of light and heavy elements, including gold and platinum, hurled into the cosmos. Two black holes merging ripple space-time itself, sending gravitational waves that stretch and compress everything in their path. We've detected these signals, heard the echoes of their final orbits through detectors like LIGO and VIRGO. Sometimes, the stars don't wait for collapse. One may simply spiral into the other, swallowed whole. In rare cases, we may witness a luminous red nova, a brilliant flash as the stars merge into one. Binary star systems show us that death isn't always sudden. Sometimes it's a long descent, a slow spiral through heat and hunger, until at last there is only one, a survivor left spinning, glowing, or gone. And in their fall, these stars tell a larger story, that even the most beautiful dances can end in collision. Deep beneath Earth's surface, molten metal flows like a slow, swirling river, a churning ocean of iron and nickel at the heart of our planet. That motion generates Earth's magnetic field, the invisible shield that protects us from solar wind, cosmic rays, and radiation. But this shield is not fixed. It drifts, it wobbles, and sometimes, in a moment of planetary instability, it flips. These are geomagnetic reversals, times when Earth's magnetic poles switch places. North becomes south. Compass needles would point the wrong way, and for a brief geological moment, the magnetic field itself becomes chaotic, weakening, or even fragmenting. Reversals are not theoretical. They've happened many times throughout Earth's history, roughly every few 100,000 years, though not on a precise schedule. The most recent complete flip, known as the Brunhes-Matuyama reversal, occurred about 780,000 years ago. Since then, the field has wandered, fluctuated, and weakened, but not yet reversed again. When a reversal happens, it doesn't occur overnight. The process can take hundreds to thousands of years, with the magnetic field weakening significantly before the flip finalizes. During this time, Earth's magnetic protection is compromised. More solar radiation reaches the surface. Auroras become more frequent and widespread, even at the equator. Satellites and communication systems, if they had existed during past reversals, would have been at serious risk. But the real concern isn't aesthetic. A weaker magnetic field means greater exposure to space radiation, which can damage the ozone layer, disrupt animal navigation, and affect electrical infrastructure. During a transition, Earth might experience multiple magnetic poles at once, scattered across the planet, a magnetic map in chaos. Some scientists believe we've already entered the early stages of a reversal. The South Atlantic Anomaly, a region where Earth's magnetic field is unusually weak, has been growing and shifting. The magnetic North Pole has also been drifting faster than expected, moving from Canada toward Siberia. Still, reversals are not extinction events. Life has survived many of them, but they are planetary scale disruptions recorded in rocks, sediments, and even ancient pottery. And when the next one comes, whether in a century or 1,000 years, it will remind us that Earth's core, though hidden, never rests. In the stillness of continents, a silent revolution brews, not of fire or impact, but of magnetism. And when the compass turns, the planet will remember. This world spins, not just on its axis, but on its field. For most of human history, asteroid impacts were the stuff of myth or mystery, fire from the sky, gods casting stones, unexplained craters. But today, we know better. We know the scars on Earth's surface. We know the story of the dinosaurs' end. And more importantly, we know that it could happen again. But for the first time in history, we're doing something about it. NASA, along with international partners, has been developing a strategy to defend Earth from hazardous near-Earth objects, NEOs, asteroids and comets whose orbits bring them close to our planet. The goal is simple in theory, but massive in scope. Find the threats before they find us, and if necessary, stop them. The first step is detection. NASA's Center for Near-Earth Object Studies, CNEOS, tracks tens of thousands of objects using ground-based telescopes and space observatories. Projects like NEOW, ISE scan the skies in infrared, detecting dark asteroids invisible to optical telescopes. But even with these efforts, we still haven't found them all, especially smaller ones, like the 50 to 140 meter objects that could devastate a city. That's why NASA is preparing to launch a new mission, NEO Surveyor, a dedicated space telescope that will search specifically for dangerous asteroids. It's designed to find 90% of near-Earth objects larger than 140 meters, the current congressional mandate, within the next decade. But detection is only part of the equation. The bigger question is, what do we do if we find one? In 2022, NASA made history with the DART mission, the Double Asteroid Redirection Test. A spacecraft deliberately slammed into a small asteroid called Dimorphos, successfully changing its orbit. It was the first real-world test of kinetic impact deflection, proving that, with enough warning time, we can alter the course of a space rock. Other options are being explored too. Gravity tractors, where a spacecraft slowly tugs an asteroid using its own gravitational pull, laser ablation, using heat to gently push an object off course, even nuclear detonations, though that remains a last resort. Planetary defense is no longer science fiction. It's engineering, strategy, and time. And it's happening now. Because space is not empty. It's full of ancient fragments left over from the birth of the solar system. And while most will miss us, it only takes one. So we watch, we prepare, and for the first time in Earth's long, scarred history, the planet is learning how to defend itself. At the end of a massive star's life, a quiet battle unfolds. Gravity pulling inward, nuclear fusion pushing outward. For millions of years, the balance holds. But when the fuel runs out, when the core can no longer resist the weight above it, the balance shatters. The star collapses, not gently, not slowly, but catastrophically. And in that collapse, the universe creates one of its most mysterious and terrifying objects, a black hole. It doesn't start with darkness. It starts with light. As the core implodes, a shockwave rips through the star, producing a supernova, a flash so bright it can be seen across galaxies. But behind the light, something stranger is forming. If the collapsing core has enough mass, typically more than 3 times that of our sun, nothing can stop the fall. Not atomic pressure, not neutron resistance. The collapse continues until matter is crushed into a single, infinitely dense point, a singularity wrapped in an event horizon from which not even light can escape. This is the birth of a stellar mass black hole. For years, black holes were theoretical, strange solutions to Einstein's equations. But now we see their fingerprints everywhere, in binary star systems, where one invisible companion pulls gas from its neighbor, heating it until it glows in X-rays. In gravitational waves, ripples in space-time created when black holes merge. In the motions of stars whipping around unseen centers, orbiting emptiness. The collapse into a black hole is not just an end, it's a transformation. The star's identity vanishes. Time and space are warped beyond recognition. From the outside, it may appear frozen, the final collapse slowed by relativity. But inside, the fall is absolute. Some stars leave behind white dwarfs, others neutron stars. But the biggest goes silent, not cold, but invisible, not dead, but unreachable. And yet, black holes are not cosmic voids of destruction. They are engines. They shape galaxies, power quasars, bend light, and hold time itself hostage. The collapse of a single star can become the anchor for entire star systems, guiding matter through gravity, not heat. When a star collapses into a black hole, it doesn't simply disappear. It becomes a new kind of presence, quiet, permanent, and strange. A place where the universe folds in on itself and dares us to understand. Not all stars end in quiet ashes. Some die in pairs, locked in slow, spiraling dances that last for billions of years. And when the moment comes, when two stellar corpses finally collide, the result is one of the most precise and powerful explosions in the cosmos, a Type Ia supernova. These supernovas don't come from massive stars collapsing under their own weight. They're born from smaller stars, the kind that live long, stable lives and die as white dwarfs, cooling embers of stellar evolution. A white dwarf is incredibly dense, about the size of Earth, but with the mass of the Sun. It has no fusion left in its core. It simply radiates heat, slowly fading away. But if a white dwarf is in a binary system, especially one with another white dwarf, the story can take a dramatic turn. Over time, the two dead stars spiral closer together. Their gravitational dance grows tighter, energy radiates away, and eventually they collide. When that happens, and the mass of the combined object crosses a critical threshold, about 1.4 times the mass of the Sun, known as the Chandrasekhar limit, something astonishing happens. The pressure and temperature rise so rapidly that the carbon and oxygen inside the white dwarf ignite in a runaway fusion reaction. But unlike a normal star, which burns gradually, this reaction consumes the entire star in seconds. There is no core collapse, no remnant, just a thermonuclear explosion that tears the star apart from within. The result is a Type Ia supernova, bright, violent, and astonishingly uniform. And that's what makes them so valuable, because these explosions occur at a predictable brightness. They serve as standard candles, cosmic mile markers. By comparing how bright they appear to how bright we know they truly are, astronomers can calculate distances across the universe. It was through observations of Type Ia supernovae that scientists discovered the accelerating expansion of the universe, leading to the theory of dark energy. So from the quiet death of two small stars comes a burst of light that reshapes our understanding of the cosmos. In that moment, time and distance reveal themselves. Two long dead stars collide, and the universe blinks, just once, brilliantly. And in that blink, we learn how far we've come and how fast everything is still moving apart. From a distance, galaxies look eternal, glowing spirals floating in darkness, elegant and serene. But galaxies are not fixed. They move, and when they meet, they don't politely pass by. They collide, they merge, they tear themselves apart, and in doing so, they reshape the universe on the grandest scale imaginable. Our own galaxy, the Milky Way, is not immune. In fact, it's already on a slow-motion collision course with its nearest large neighbor, the Andromeda Galaxy, 2 million light-years away and getting closer every second. The two galaxies are expected to collide in about 4.5 billion years. It won't be a crash in the traditional sense. The stars inside each galaxy are so far apart that direct collisions between them will be rare. But gravity will pull, twist, and warp both galaxies, ripping away spiral arms, flinging stars into new orbits, and eventually merging the two into a single, massive elliptical galaxy, sometimes referred to as Milkomeda. This isn't a violent end for stars, but it is a cosmic upheaval. Supermassive black holes at the centers of both galaxies will spiral together and merge, sending out gravitational waves across the universe. Gas clouds will be compressed, triggering intense bursts of new star formation, starbursts that briefly light up the merging system. Some stars may be ejected entirely, thrown into intergalactic space at extreme speeds. Galaxy collisions are common in the universe. In fact, they're part of how galaxies grow. Many of the largest galaxies we see today are the result of past mergers, stitched together by the gravity of smaller systems long absorbed. And they don't just change shape, they change fate. Collisions can activate dormant black holes, ignite quasars, and alter the structure of entire galactic clusters. We've observed these events in every stage, from first contact to warped mid-mergers to fully blended remnants. The Hubble and James Webb Space Telescopes have captured snapshots of these titanic encounters across billions of years, each one telling part of the story of how galaxies live and die. And when the Milky Way and Andromeda finally meet, Earth may still be here. Our sky will transform, filling with streams of new stars, warped arms, and glowing gas. For 1 billion years, the night will shift, shimmer, and change. And though we may not survive to see it, the galaxy we call home will be reborn, not destroyed, but transformed. Not an end, but a new beginning written in stars. Most black holes stay anchored, nestled at the centers of galaxies, or quietly orbiting as the remnants of collapsed stars. But not all of them follow the rules. Some black holes are wanderers, drifting, invisible, alone. These are rogue black holes, and they may be quietly moving through the cosmos, including our own galaxy, right now. A rogue black hole is born when violence severs its ties. Sometimes it's ejected during the chaotic merger of two galaxies, flung outward by gravitational recoil after two supermassive black holes collide and merge. Other times, it's the result of a failed stellar core collapse, where the explosion kicks the newborn black hole with enough velocity to escape its stellar neighborhood, or even the entire galaxy. Once loose, a rogue black hole moves silently through space. It emits no light, no heat, no radiation, unless it happens to pass through a region with gas or dust to devour. Most of the time, it doesn't. It is simply darkness in motion, a gravity well wrapped in silence. Detecting such objects is notoriously difficult. They don't glow, they don't cast shadows, but they do bend light. In 2022, astronomers reported one of the most promising candidates yet, a potential stellar mass black hole drifting through the Milky Way, detected via gravitational microlensing. When the black hole's gravity briefly magnified the light of a background star as it passed in front of it. This was a subtle, delicate observation, but a powerful proof of concept. It means we can, with patience and precision, begin to track the invisible. Rogue black holes may be far more common than we think. Some estimates suggest that millions of them could be drifting through the Milky Way alone, each a ghost of a once living star. Most will never come close to a planet or star, but if one did, the results would be catastrophic. Its gravity could disrupt orbits, pull apart moons, or even swallow entire solar systems, quietly, efficiently, without a sound. And yet, most will never touch anything at all. They roam the galaxy not as predators, but as relics, evidence of the chaos that shaped the early universe. They are the shadows that move, and somewhere out there between stars, they are still drifting, cold, undetected, and waiting. Before Hubble, space looked blurry. Astronomers on Earth stared through turbulent air, peering past the distortions of our own atmosphere. Stars twinkled, yes, but that shimmer was an obstacle, not a gift. Then in 1990, a school bus-sized telescope was launched beyond that atmosphere into low Earth orbit, where it could finally see the universe with unprecedented clarity. That telescope was the Hubble Space Telescope, and nothing in astronomy would be the same again. At first, it seemed like a disaster. Hubble's primary mirror had a tiny flaw, just 2 microns off, but enough to blur every image. The public mocked it. Congress debated killing it, but in 1993, astronauts flew up to Hubble and installed a set of corrective optics, the equivalent of giving glasses to the telescope. And from that moment on, Hubble began to show us the universe as we had never seen it. Galaxies in collision, stars being born, light from the early universe, stretching across time. It was Hubble that gave us the famous Pillars of Creation image, towering clouds of dust in the Eagle Nebula. It was Hubble that performed the Hubble Deep Field, pointing at an apparently empty patch of sky for 10 days and revealing thousands of hidden galaxies, each teeming with stars. And Hubble didn't just take pictures. It helped measure the expansion rate of the universe. It identified exoplanet atmospheres. It observed supernovas, black holes, and the aftermath of cosmic collisions. For more than 3 decades, it operated above us, serviced and upgraded by astronauts on the space shuttle. It became not just a tool, but a symbol of vision, of clarity, of cosmic ambition. Even today, with newer telescopes in service, Hubble continues to operate. It still sends back images, still contributes to research, still reminds us of what happens when a civilization decides to look beyond its world. In many ways, astronomy split into 2 eras, before Hubble and after. And even now, orbiting 540 kilometers above our heads, Hubble remains one of the greatest scientific instruments ever built. If Hubble opened our eyes, the James Webb Space Telescope opened a new sense entirely. Launched in December 2021, after years of delays and engineering challenges, Webb was designed not to replace Hubble, but to extend our vision farther, deeper, and into wavelengths of light no human eye can see. Unlike Hubble, which orbits Earth, Webb was sent far beyond the Moon, nearly 1.5 million kilometers away, to a stable point known as L2. There, shielded from the sun by a massive tennis court-sized sun shield, it can observe the coldest, faintest objects in the universe. Webb's specialty is infrared light, radiation, just beyond the red edge of the visible spectrum. Infrared lets us see what's hidden: the earliest galaxies, shrouded in cosmic dust, the birthplaces of stars and planets, the light from the dawn of time, stretched and cooled by billions of years of cosmic expansion. Its mirror, made of 18 gold-coated hexagonal segments, is over 6.5 meters across, more than twice the size of Hubble's. Its sensors are tuned to such sensitivity that Webb can detect the chemical fingerprints in the atmospheres of exoplanets, including water vapor, carbon dioxide, and methane. Just months after deployment, Webb delivered its first images, not just beautiful, but revolutionary. A galaxy cluster acting as a gravitational lens, bending the light of even older galaxies behind it. Clouds of gas swirling in star-forming regions. The spectral signature of an exoplanet's atmosphere, hinting at a world with clouds and possibly even a water cycle. But it's not just the data, it's the perspective. James Webb is a time machine. It sees things not as they are, but as they were billions of years ago. It lets us look back to the era when the first galaxies assembled, to the moments when light itself was still new. Where Hubble gave us beauty and clarity, Webb adds depth, a sense that the universe is not only large, but ancient, layered, and full of mysteries just starting to come into focus. It's not the final telescope, but it may be the most important one we've ever built. In the summer of 1977, 2 spacecraft were launched with a mission unlike any before to explore the outer planets of the solar system, and then, if all went well, to keep going. They were called Voyager 1 and Voyager 2, and they were designed for durability, not elegance. Small, rugged, and powered by radioactive plutonium, these twin spacecraft carried instruments, cameras, and a golden phonograph record, the famous Voyager Golden Record, encoded with music, greetings, and sounds of Earth. No one expected them to last this long. Voyager 1 flew past Jupiter in 1979, sending back images of the planet's swirling clouds and volcanic eruptions on Io, the first time active volcanism was ever seen beyond Earth. A year later, it passed Saturn, capturing the stunning structure of its rings and revealing moons that had never been seen in detail. Voyager 2, taking a slightly different route, added 2 more firsts. It became the only spacecraft to visit Uranus and Neptune, discovering strange magnetic fields, ice giant weather patterns, and rings around planets where we never expected them. But the most remarkable part of the Voyager missions began after the planetary flybys. Instead of shutting down, they kept going. Voyager 1 crossed the boundary of the heliosphere, the bubble of solar wind surrounding our system, and entered interstellar space in 2012. Voyager 2 followed in 2018. They are now the farthest human-made objects from Earth, over 20 billion kilometers away, and still communicating. Every now and then, they send back data, measurements of cosmic rays, interstellar particles, and the shape of the solar system's edge. Tiny packets of information traveling for over 20 hours across the vast dark. The Voyagers also gave us a new perspective on home. In 1990, Voyager 1 turned its camera back toward Earth at Carl Sagan's request and took the iconic image known as the pale blue dot, a tiny speck of light suspended in a sunbeam. It reminded us how small we are and how far we've come. Today, the Voyagers are slowly going silent, one instrument at a time. But even as their signals fade, their legacy endures. They were not just explorers of the solar system. They were messengers, sent not just to planets, but to time itself. When it launched in 1997, Cassini was just another spacecraft with a long journey ahead. But when it arrived at Saturn 7 years later, it transformed into something else entirely, a window into one of the most mysterious regions of the solar system. For over 13 years, Cassini orbited Saturn, becoming one of the most productive and awe-inspiring missions NASA and the European Space Agency ever launched. It wasn't just the rings, although Cassini captured them in breathtaking detail, revealing their structure, thickness, and strange behaviors like spokes and waves that ripple through icy particles. It wasn't even just Saturn itself, with its massive storms, hexagonal polar vortex, and rapid rotation. What made Cassini extraordinary was the unexpected. Cassini carried with it a lander, Huygens, which detached in 2005 and descended to the surface of Titan, Saturn's largest moon. For the first time in history, we landed something on a world beyond Mars. And what it showed was stunning. A frozen landscape with lakes, rivers, and rain made of methane, and an atmosphere dense with organic chemistry. Titan looked alien, but strangely familiar. Then came Enceladus, a small, icy moon, once thought to be inert. But Cassini's instruments detected plumes of water vapor erupting from its south pole, geysers shooting into space through cracks in the ice. Cassini flew through those plumes, and inside them it found organic molecules, salt, and signs of warm, liquid water beneath the surface, suggesting a hidden ocean, possibly habitable. Cassini showed us that even in the cold, far reaches of the solar system, there are places where life might exist. Not in the way we imagined, not green fields or forests, but in oceans beneath ice, warmed by tidal forces and chemical energy. Its final mission was poetic. In 2017, with fuel running low, Cassini was directed to dive into Saturn's atmosphere, a planned destruction to avoid contaminating any potentially life-bearing moons. As it descended, it kept sending data until the very last moment, becoming one with the planet it had studied for more than a decade. Cassini didn't just explore Saturn, it redefined what we thought the outer solar system could be. Not empty, not lifeless, but dynamic, evolving, and full of possibilities. For most of human history, we didn't know if other planets existed beyond our own solar system. It wasn't that we thought Earth was alone. We just had no proof, no evidence, no way to see them. That changed in 2009 when NASA launched the Kepler Space Telescope, a mission so precise and so patient that it quietly rewrote the boundaries of what we believed. Kepler didn't look for planets the way you might think. It didn't take photographs of alien worlds. Instead, it stared at a single patch of sky filled with about 150,000 stars and waited for tiny dips in brightness, the telltale signs of a planet passing in front of its star, a technique called the transit method. Over the course of its mission, Kepler detected over 2,600 confirmed exoplanets and thousands more possible candidates. Some were massive gas giants, close to their stars. Some were rocky. Some orbited in their star's habitable zone, where temperatures might allow for liquid water. But it wasn't just the numbers. It was the realization that planets are common, that most stars likely have them, that Earth is not rare, but perhaps typical, and that the Milky Way may contain billions of Earth-like worlds. Kepler found planets that orbit two stars, like Tatooine, planets with year lengths of just a few days, and some so distant from their stars that their orbits stretch for decades. And the telescope faced challenges. In 2013, it lost two of its four reaction wheels, essential for pointing. But engineers reprogrammed the mission, creating K2, a second phase that allowed Kepler to continue observations using solar pressure for balance. Even after its retirement in 2018, Kepler's data is still yielding discoveries. Astronomers continue mining its archive for signals, and its legacy lives on in every exoplanet found today. Kepler didn't just find planets, it opened a door. A quiet, steady sentinel that showed us our night sky is filled with other worlds, some perhaps like our own, waiting to be understood. When Kepler's mission came to an end, it didn't leave behind a void. It passed the torch, and the telescope that caught it was TESS, the Transiting Exoplanet Survey satellite, launched in 2018 with a bold new ambition to search the entire sky. Unlike Kepler, which focused on one patch of stars, TESS was designed to be broad and fast. It divides the sky into sectors, observing each one for nearly a month, covering 85% of the sky over 2 years. Its goal? To find planets around the brightest, nearest stars, the ones we might study up close someday. Like Kepler, TESS uses the transit method, looking for dimming light as a planet crosses in front of its star. But because its targets are closer and brighter, astronomers can follow up with ground-based telescopes and powerful instruments like the James Webb Space Telescope, probing atmospheres and searching for biosignatures. TESS has already discovered thousands of candidate exoplanets, including super-Earths, mini-Neptunes, and even planets in multi-star systems. Some orbit stars just dozens of light years away, cosmic neighbors by galactic standards. One of TESS's strengths is speed. Its cameras capture wide fields with high cadence, allowing it to catch short-period planets, ones that orbit quickly and offer frequent transits. That means confirmation comes faster, data comes faster, and discoveries stack up faster. But TESS isn't just about exoplanets. Its constant monitoring of bright stars has made it valuable for stellar physics, variable stars, supernovae, and even the detection of asteroseismic activity, the gentle pulsations that reveal a star's internal structure. In some ways, TESS feels like a bridge. It connects the era of Kepler's deep stare to a future of precision spectroscopy, direct imaging, and atmospheric analysis. It scouts targets that larger telescopes will study in detail. TESS reminds us that the search for other worlds isn't slowing down. It's accelerating, spreading across the sky, star by star, light curve by light curve. The more we look, the more we find. And TESS ensures we don't miss what's right in front of us. Most space missions look outward, towards stars, planets, galaxies beyond. But some of the most vital telescopes look inward, toward the one star we can't live without. The Solar and Heliospheric Observatory, or SOHO, is one of them. Launched in 1995, SOHO was a joint project between NASA and the European Space Agency, designed not just for solar science, but for space weather forecasting, a concept that would grow more critical with every passing year. Orbiting around the Lagrange point L1, about 1.5 million kilometers from Earth, SOHO has a continuous, uninterrupted view of the Sun. It observes everything from the surface of the Sun to the solar wind, the stream of charged particles that flows outward across the solar system. SOHO's primary mission was to study the Sun's interior and atmosphere. It uses helioseismology, the study of sound waves traveling inside the Sun, to map its internal dynamics. It captures the structure of the corona, the outer atmosphere that mysteriously burns hotter than the surface, and it tracks coronal mass ejections, or CMEs, immense bursts of plasma and magnetic fields that can slam into Earth, disrupting satellites, power grids, and communications. Thanks to SOHO, we've learned how to predict solar storms. It acts as an early warning system, giving us precious minutes or hours to protect vulnerable infrastructure. But SOHO also became something unexpected, a comet hunter. Its instruments, designed to monitor the solar environment, have detected over 4,000 comets, many of them sun grazers, icy bodies that swing perilously close to the Sun and often disintegrate. SOHO wasn't meant to last this long, yet decades later, it's still operational, still watching, still feeding scientists with real-time solar data, which not only protects Earth, but deepens our understanding of the star that fuels our climate, drives our weather, and defines the rhythm of life on this planet. In a way, SOHO reminds us that our sun is not a steady flame, but a dynamic, restless sphere of fusion, pulsing with cycles, storms, and sudden bursts of energy. And in watching it closely, we're not just doing science. We're learning how to live safely in the shadow of a star. Most of the universe is invisible to human eyes. We see only a narrow sliver of the electromagnetic spectrum, the same way an old piano plays just a few keys of an infinite keyboard. But some of the most violent, mysterious, and energetic phenomena in the cosmos play in the high, bright notes of X-rays. To hear them, we needed a new kind of telescope. We built Chandra. Launched by NASA in 1999 aboard the Space Shuttle Columbia, the Chandra X-ray Observatory was unlike any telescope before it. It wasn't about stars and galaxies in the usual sense. It was about neutron stars, black holes, supernova remnants, and the glowing gas in galaxy clusters that no other telescope could fully reveal. Chandra had to be placed in a high elliptical orbit, far above Earth's atmosphere, because X-rays from space don't reach the ground. Its orbit takes it 1/3 of the way to the moon, allowing for long, uninterrupted observations. Its optics are equally unusual. Unlike visible light telescopes that use mirrors to reflect light directly, Chandra's X-ray mirrors are nested in concentric cylinders, angled to graze incoming X-rays, focusing them delicately without absorbing their energy. The results have been stunning. Chandra revealed the structure of supernova remnants, like the famous Cassiopeia A, exposing shock waves and high-energy particles. It observed the jets of matter launched from black holes, moving at near light speed. It showed that galaxy clusters are filled with hot, X-ray emitting gas, evidence of dark matter sculpting their shapes. It also deepened our understanding of our own galaxy, imaging the chaotic center of the Milky Way, where a supermassive black hole silently shapes the motion of stars. Perhaps most importantly, Chandra made the invisible visible. It showed that the universe is not quiet. It is active, energetic, explosive, and constantly in motion, even when seen through the cold, sterile light of high-energy radiation. Even after more than 2 decades in space, Chandra remains the most sensitive X-ray telescope ever built. It doesn't show us beauty in the classical sense, but it reveals the bones and fire of the cosmos, the engines that power the galaxy and leave behind the ashes of creation. If Chandra gave us X-rays and Hubble gave us visible light, then Spitzer let us see the universe in a glow we rarely think about, the infrared. It was a telescope built not to see what shines, but what radiates, what lingers with warmth, even in the coldest reaches of space. Launched in 2003, the Spitzer Space Telescope was the final member of NASA's Great Observatories program, joining Hubble, Chandra, and Compton. Its specialty was infrared astronomy, and that meant seeing what lies behind dust, beneath the surface, and beyond the reach of ordinary light. Infrared light is the domain of cool stars, stellar nurseries, planet-forming disks, and distant galaxies whose light has been stretched by cosmic expansion. And because Earth's atmosphere absorbs most infrared radiation, Spitzers had to operate in space and stay cold, very cold. To do its job, Spitzer was chilled with liquid helium, reaching temperatures just a few degrees above absolute zero. Only then could it detect the faint heat signatures coming from billions of light years away. Spitzer discovered exoplanet atmospheres long before JWST. It mapped dusty disks where planets were forming. It revealed the structure of our own Milky Way, hidden behind veils of interstellar dust, and it peered deep into galaxy clusters, identifying some of the most distant galaxies ever observed at the time. One of its most iconic discoveries came not from galaxies, but from a single compact system, TRAPPIST-1, a star with 7 Earth-sized planets, some of them potentially habitable. Spitzer's precise measurements helped characterize their orbits, sizes, and possible compositions, setting the stage for future study. Spitzer was decommissioned in 2020 after 16 years of operation, far longer than expected. Its infrared eyes faded, but its legacy remains. It taught us that heat lingers where we least expect it, that the young, the hidden, and the ancient all emit their quiet warmth, and that sometimes, to see the universe most clearly, you have to look where the light doesn't shine, but where it still softly glows. Imagine trying to map a forest while standing inside it, not just its shape, but the position and motion of every tree. That's what Gaia set out to do for our galaxy. Launched by the European Space Agency in 2013, Gaia is a quiet spacecraft with an enormous task to create the most detailed 3D map of the Milky Way ever attempted. Not a photograph, not an impression, a census of stars measured with exquisite precision. Gaia orbits around Lagrange point L2, a gravitationally stable spot about 1.5 million kilometers from Earth. There, it scans the sky methodically, tracking the position, distance, motion, and brightness of stars again and again over years. Its instruments can detect minute shifts in a star's position, the width of a human hair seen from 1,000 kilometers away. From this, Gaia calculates not just where stars are, but how they move, how fast, and even how old they might be. The result? A revolution in stellar cartography. Gaia has mapped over 2 billion stars, along with hundreds of thousands of asteroids, exoplanets, quasars, and distant galaxies. It revealed that the Milky Way is not a calm, flat disk, but a writhing, dynamic structure, rippled by ancient collisions with smaller galaxies. It showed how stars stream through space in families, moving groups, clusters, and remnants of galactic mergers. We've also learned about the mass and shape of the Milky Way, the motion of its arms, and the location of mysterious features like the galactic warp, a bend in the disk that twists like a ripple on a pond. Gaia's data feeds into almost every branch of astronomy. It's used to calibrate distances to supernovas, to track rogue stars flung from the galactic center, to study the dark matter halo that invisibly cradles our galaxy. It's not a flashy mission. There are no close-up images or dramatic discoveries. But Gaia is a foundation, a quiet, steady observer, transforming our understanding of where we are and where we're going. In mapping the Milky Way, Gaia gives us a context, a place in the stars, a home not just in space, but in motion. For most of its life, Pluto was a blurry smudge, distant, cold, and poorly understood. Even after decades of planetary exploration, it remained an enigma, orbiting in the frozen reaches of the Kuiper Belt. But in 2015, all of that changed. Enter New Horizons, a piano-sized NASA spacecraft that traveled more than 4.8 billion kilometers to give us our first ever close-up look at Pluto. Launched in 2006, New Horizons spent nearly a decade coasting through deep space, passing by Jupiter in a slingshot maneuver that shaved years off its journey. And when it finally arrived at Pluto in July 2015, the images it sent back stunned the world. We had expected a gray, lifeless rock. Instead, we found a world with a beating heart, quite literally. A vast, icy plain in the shape of a heart, named Tombaugh Regio, dominated the landscape. It was not static, it was active. Pluto has glaciers, mountains made of water ice, and possibly even cryovolcanoes. Its thin atmosphere expands and contracts as it moves along its elliptical orbit. It's a small world, yes, but one that challenges everything we thought we knew about geological activity on cold, distant bodies. But New Horizons didn't stop there. After Pluto, it ventured further into the Kuiper Belt, targeting a small ancient object called Arakoth. This contact binary, two icy lobes fused together, offered a glimpse into the early building blocks of the solar system. Arakoth is pristine, unchanged for over 4 billion years, and gave scientists a rare look at how planets may have formed from smaller bodies. New Horizons is still moving outward, carrying with it a small amount of Pluto's dust, a digital library of human culture, and the hopes of a species forever curious. Its instruments continue to study the environment at the edge of the sun's influence, the heliopause, the Kuiper Belt, and the transition into interstellar space. With each passing year, it adds new data to our understanding of the solar system's frontier. New Horizons wasn't just about Pluto. It was about the idea that no world is too far, too small, or too obscure to be worth exploring. Even on the coldest edge of sunlight, there are stories waiting to be told. For as long as we've known about black holes, they've lived in the realm of theory, invisible monsters, predicted by Einstein, suspected by observation, but never seen. By definition, nothing escapes them, not even light. So how do you take a picture of the unseeable? In 2019, the world witnessed a scientific milestone, the first ever image of a black hole's shadow, captured by a project called the Event Horizon Telescope, or EHT. But the EHT isn't a single telescope. It's a global network of radio observatories, synchronized to act as one Earth-sized eye. From the Atacama Desert to Hawaii, from Greenland to the South Pole, each telescope records its slice of the sky. The data is so massive it can't be sent digitally. It has to be physically shipped on hard drives and processed together with atomic clock precision. The target? Messier 87, a giant elliptical galaxy 55 million light-years away, home to a supermassive black hole with a mass of 6.5 billion suns. The result was iconic: a glowing ring of gas, heated to billions of degrees, orbiting a dark center, the event horizon, the point of no return. It wasn't a photo in the conventional sense. It was a reconstruction, the result of complex algorithms and years of collaboration between hundreds of scientists. But it confirmed what Einstein's theory had predicted, and it gave us our first real glimpse of the warping of space itself. Since then, the EHT has turned its gaze to other targets, including the black hole at the center of our own galaxy, Sagittarius A star. That image, released in 2022, showed a smaller, more chaotic ring, confirming once again that black holes are not science fiction. They are very real and very powerful. But the EHT is about more than just pictures. It allows scientists to test general relativity in extreme conditions. It provides insights into accretion disks, relativistic jets, and the behavior of matter at the edge of physics. It's helping us understand how galaxies evolve and how their hearts, often hidden, drive so much of what we see. The Event Horizon Telescope didn't just photograph a black hole, it made the invisible visible. It gave form to the abyss, and it reminded us that even the darkest corners of the universe are not beyond our reach. Most telescopes focus on stillness. They stare at one point in the skies for hours, days, even years, waiting for the faintest signals from the past to appear. But what if we built a telescope to do the opposite, to watch everything all at once, over and over again? That's the vision behind the Vera Rubin Observatory, a groundbreaking facility nearing completion in Chile. When operational, it will become the first telescope to survey the entire visible southern sky every few nights, not in snapshots, but in motion. At the heart of the observatory is the LSST camera, the largest digital camera ever built for astronomy. It weighs over 3 tons and boasts a resolution of 3.2 gigapixels. Each image it captures will cover an area of sky equivalent to 40 full moons, and it will do this every 30 seconds, night after night, for 10 years. This isn't just about making beautiful pictures. The Rubin Observatory is a time-domain telescope, a machine designed to capture the changing universe. It will detect supernovas the moment they explode, track asteroids that could pose a threat to Earth, and spot the subtle flickers that reveal exoplanets, black hole activity, or the gravitational tugs of dark matter. Over its 10-year mission, the observatory will build the most detailed 4D map of the universe ever created, tracking billions of objects, not just in space, but through time. one of its most ambitious goals, to help unravel the mystery of dark energy, the force driving the accelerated expansion of the universe. By charting how galaxies move and cluster over billions of years, the Rubin Observatory may give us our clearest insight yet into the structure of space-time itself. It's named after Vera Rubin, the astronomer whose observations of galactic rotation first suggested the existence of dark matter. A fitting tribute for a telescope that, like Rubin, is determined to show us that the universe is not static, but alive with motion and mystery. When it begins full operation, the Vera Rubin Observatory will not be watching one thing. It will be watching everything. And in doing so, it may change not just what we see, but how we see it. For over a century, gravitational waves were a mathematical whisper, a strange prediction of Einstein's general relativity. He thought they were real, but doubted we'd ever detect them. After all, how could you measure ripples in the very fabric of space-time? And yet, in 2015, a faint signal traveled across the cosmos and gently nudged a pair of mirrors on Earth. The world changed in that moment because LIGO, the Laser Interferometer Gravitational Wave Observatory, had heard the universe ring. At its core, LIGO is a deceptively simple machine. 2 long tunnels, each 4 kilometers in length, arranged in an L shape. Inside, laser beams bounce between mirrors, measuring the distance to within 1/10,000th the width of a proton. When a gravitational wave passes, it stretches space in one direction and compresses it in another, ever so slightly changing the length of the arms. It's a measurement so delicate that seismic noise, passing trucks, even thermal motion can interfere. That's why LIGO is so meticulously isolated, and why there are 2 detectors, one in Louisiana, one in Washington State, to confirm any true cosmic event. The first detection: 2 black holes merging 1.3 billion light years away. Their collision sent out gravitational ripples that reached us as a fleeting tremor in space-time. We didn't see it, we heard it. That chirp confirmed a century-old theory and opened an entirely new way of observing the universe through gravity itself. Since then, LIGO, joined by its European counterpart Virgo, has detected dozens more events. Black hole mergers, neutron star collisions, and even mixed systems that defy our expectations. One neutron star merger was also observed by traditional telescopes, a multi-messenger event that revealed not only gravitational waves, but light, gamma rays, and even heavy elements like gold and platinum being forged in the explosion. LIGO showed us that the universe is not silent. It vibrates, and those vibrations carry stories of cataclysm and creation, of massive objects warping space, of time itself being stirred. And we've only just begun to listen. With upgrades and next generation observatories like LISA on the horizon, gravitational wave astronomy promises to reveal things no telescope ever could. Because some secrets don't shine, some secrets echo. For years we waited, through delays, redesigns, and an anxious launch into the deep black of space. But when the James Webb Space Telescope, JWST, unfolded its golden mirrors and turned its gaze to the cosmos, the wait proved worth every second. Its first light images, released in July 2022, didn't just impress. They redefined what we thought possible in astronomy. The very first image, known as Webb's first deep field, showed a speck of sky no larger than a grain of sand held at arm's length. And yet, in that tiny sliver, there were thousands of galaxies, some stretching back over 13 billion years, distorted into graceful arcs by gravitational lensing. We weren't just looking far, we were looking deep into cosmic time. Another image captured the Carina Nebula, a vast stellar nursery where new stars are born. But unlike Hubble's ethereal blues and purples, Webb revealed towers of gas and dust glowing in infrared, showing stars forming within the clouds, places Hubble simply couldn't penetrate. Then came Stephan's Quintet, a group of interacting galaxies. Webb captured not only the dramatic collisions and streams of stars, but also the hidden details of dust and shock waves, the fingerprints of galactic evolution. And perhaps most striking, the image of the Southern Ring Nebula, the glowing shell of a dying star. Where past telescopes saw a fuzzy cloud, JWST resolved it into nested layers of gas, complex, structured, and heartbreakingly beautiful. But JWST didn't just send pictures. It also delivered spectroscopy, the ability to break light into its components and analyze the atmospheres of distant exoplanets. In one of its early triumphs, Webb detected water vapor in the atmosphere of K2-18b, a potentially habitable exoplanet, and found hints of carbon-bearing molecules, key to life as we know it. These first light images were more than pretty postcards. They were proof of concept, a demonstration of power. That JWST wasn't just a successor to Hubble, it was a leap forward into a new era. It sees the cold, the dusty, the distant, and the first. It sees what has never been seen. And with every image, it expands our view, not only of the universe, but of what we're capable of imagining. By the time Perseverance landed on Mars in 2021, NASA had already sent multiple rovers to the Red Planet. So what made this one different? The answer lies not just in the rover itself, but in the tiny helicopter it brought along. Perseverance is the most advanced robotic explorer ever sent to another world. Its mission? To seek signs of ancient life, collect samples for return to Earth, and test technologies for future human missions. But even with all its instruments, drills, and cameras, one of the boldest experiments was just 1.8 kilograms in size. That was Ingenuity, the first aircraft to fly on another planet. Flying on Mars is no easy feat. Its atmosphere is just 1% as dense as Earth's, making lift incredibly difficult. Yet in April 2021, Ingenuity rose into the thin Martian air, hovered, turned, and landed. With that, powered flight became interplanetary. Ingenuity was supposed to fly just 5 times. Instead, it flew dozens of missions, scouting terrain, testing flight in extreme conditions, and even helping guide Perseverance by mapping safe routes. It became not just a demonstration, but an essential partner. Meanwhile, Perseverance itself began a groundbreaking journey across Jezero Crater, an ancient lakebed believed to have once held water and possibly life. It drilled into Martian rock, cached samples in sealed tubes, and began the search for biosignatures, chemical clues that may hint at microbial life from billions of years ago. Perseverance also tested tools for the future. An experiment called MOXIE converted Martian CO2 into oxygen, a vital step for future astronauts. Its navigation systems used artificial intelligence to drive more safely and autonomously than any rover before it. Together, Perseverance and Ingenuity represent a new phase of exploration. Not just robotic scouting, but preparation for human presence. Not just static observation, but mobility and adaptability. They are the first steps in a plan to bring pieces of Mars back to Earth, and eventually, perhaps, to send humans there. And in every wheel track and whirring rotor, they remind us the boundary between possible and impossible is thinner than we think. Sometimes, all it takes is a little perseverance and a touch of ingenuity. Every great telescope we've launched has changed us. Hubble gave us the age of galaxies. Kepler gave us a universe of planets. Webb opened windows into the early cosmos. But what comes next? The future of astronomy lies in missions we've only begun to dream about. Projects like LUVOIR, HABEX, and other next-generation observatories that could redefine what it means to see the universe. Let's start with LUVOIR, the Large Ultraviolet Optical Infrared Surveyor. It's designed to be a kind of super Hubble, far larger and more powerful, with a mirror up to 15 meters across, nearly 5 times the diameter of JWST. LUVOIR would be capable of imaging Earth-like exoplanets around Sun-like stars, detecting biosignatures like oxygen, methane, and water vapor in their atmospheres. But le voir isn't just about planets. It could map galaxies with unprecedented resolution, observe the formation of stars and black holes, and study cosmic structure on a grand scale. Its versatility would make it one of the most ambitious scientific instruments ever conceived. Then there's Habex, the Habitable Exoplanet Observatory. More specialized than le voir, its mission is focused: find other Earths. Habex would use a starshade, a massive flower-shaped disk flying tens of thousands of kilometers ahead of the telescope, blocking starlight so faint planets can be seen beside their suns. Together, these missions aim to answer perhaps the biggest question in astronomy: are we alone? But even beyond those, there are ideas taking shape. LISA, the Space-Based Gravitational Wave Observatory. Origins, designed to peer into the dusty birthplaces of stars and planets. And radio arrays on the moon's far side, shielded from Earth's interference. Each of these represents a shift, not just in capability, but in perspective. We're no longer content with glimpsing light from the past. We want to read the chemistry of alien skies. We want to hear the tremors of space-time. We want to search with intent. These future tools are not just instruments, they're acts of hope. They require decades of planning, international cooperation, and a willingness to invest in questions that may not have answers yet. But that's what astronomy is: a long, slow pursuit of clarity, of reaching farther, listening harder, and seeing what no one has seen before. The next great discovery may not come from a flash in the sky, but from the patient gaze of a machine we haven't built yet. And when we look back at this moment, we may realize this was the dawn of a new age of seeing. High in the Chilean Andes, where the air is dry, thin, and still, there sits a forest of white radio dishes, not aimed at the earth, but at the vast sky above. This is ALMA, the Atacama Large Millimeter/Submillimeter Array, and it doesn't see stars. It sees the places where stars are born. Unlike optical telescopes, which capture visible light, ALMA listens to some of the coldest and faintest signals in the universe, light at millimeter and submillimeter wavelengths. This light comes not from blazing suns or glowing galaxies, but from dust and gas, the raw ingredients of stars, planets, and even life itself. ALMA is made of 66 individual antennas spread across a desert plateau at 5,000 meters altitude. Each antenna can move, allowing the array to change its configuration like a zoom lens stretching across miles. Together, they act as one enormous telescope with remarkable resolution, able to peer into dense clouds that would block any ordinary view. What it sees is remarkable. ALMA has imaged protoplanetary disks around young stars, swirling structures where new planets are forming. It's revealed rings and gaps, signs of baby planets carving out paths in their dusty cradles. For the first time, we can observe not just the theory of planetary formation, but its actual process. ALMA also maps the chemistry of interstellar clouds, detecting complex organic molecules, precursors to amino acids and life in places where stars haven't even formed yet. It studies colliding galaxies, watching how gas compresses and ignites new waves of star birth. And it captures the faint whispers of galaxies at the edge of the observable universe, letting us look back billions of years. Its location, far from civilization, minimizes interference. Its precision, down to fractions of a millimeter in wavelength, opens a window into a universe we never knew we could see. ALMA doesn't show us the stars themselves. It shows us where they come from, the cold, dark nurseries that eventually light up the sky. And in doing so, it reminds us that even in silence and shadow, the universe is preparing its next act. For most of human history, the sun was untouchable, a blazing godlike presence in the sky, too bright to stare at, too hot to approach, too powerful to fully understand. But in 2018, NASA launched a mission that dared to cross a line no spacecraft had ever crossed before. Its name was the Parker Solar Probe, and its mission was simple yet bold: touch the sun. Named after solar physicist Eugene Parker, who first theorized the solar wind, the probe was built to dive into the sun's outer atmosphere, or corona, to understand what powers the solar wind and why the corona is millions of degrees hotter than the sun's surface. To survive the journey, Parker had to be engineered like no spacecraft before it. Its thermal shield is made of carbon composite foam, only 11 centimeters thick, but capable of withstanding temperatures over 1,400 degrees Celsius. Just behind that shield, the instruments stay at room temperature, in a pocket of calm amid the inferno. But it's not just heat that Parker endures. It flies at incredible speed, over 600,000 kilometers per hour, making it the fastest human-made object in history. And each orbit brings it closer to the sun, with repeated gravity assists from Venus gradually shrinking its path. As it dives into the corona, Parker measures magnetic fields, solar particles, plasma flows, and waves rippling through the solar atmosphere. It captures real-time solar wind data, helping scientists understand how the sun's energy escapes into space and how that energy can affect Earth. Already, Parker has rewritten what we thought we knew. It detected magnetic switchbacks, sudden reversals in the Sun's magnetic field. It flew through the Alphen critical surface, the boundary where the solar wind becomes faster than the speed of wave propagation, effectively crossing into the Sun's atmosphere. This isn't just about solar science. Understanding the Sun's behavior helps us protect satellites, astronauts, and power grids from solar storms. It informs the future of space travel and space weather prediction. The Parker Solar Probe is still diving, still braving the light, still teaching us that even the most familiar object in the sky is full of secrets. It is, quite literally, a mission that brings us closer to our star than ever before. Jupiter is a planet of superlatives, the largest in the solar system, the fastest spinning, the one with the most moons, the strongest magnetic field, the wildest storms. For centuries, we saw its swirling clouds and giant red spot, but we didn't know what lay beneath. In 2016, that changed with the arrival of Juno, a NASA mission designed to unlock the secrets hiding beneath Jupiter's turbulent atmosphere. Unlike previous spacecraft that orbited far from the gas giant, Juno was built to fly closer than ever before, dipping into tight, elongated polar orbits that take it just a few thousand kilometers above Jupiter's cloud tops. From this vantage point, Juno collects data no other probe ever could. It maps gravitational variations to probe the deep interior. It measures magnetic fields to study Jupiter's powerful dynamo. It tracks microwave radiation to peer beneath the cloud layers, revealing a world of ammonia storms, jet streams, and chaotic circulation patterns. One of Juno's key questions: does Jupiter have a core? Early theories suggested a solid, rocky center, but Juno's data points to something stranger, a fuzzy, diluted core, possibly the result of a giant impact early in Jupiter's life. Juno also revealed that Jupiter's famous Great Red Spot is much deeper than expected, extending over 300 kilometers down, with swirling roots that penetrate the atmospheric layers. And then there's Jupiter's auroras, the largest in the solar system. Juno has shown that they're powered not just by solar particles, but by Jupiter's own rotation and magnetic environment, which whip plasma around the planet like an electric dynamo. Even the planet's moons have come into sharper focus. Juno has taken close-up images of Ganymede and Europa, preparing the way for future missions like Europa Clipper. With its solar panels stretched wide and its instruments hardened against radiation, Juno orbits a planet more massive than all the others combined. It doesn't just study Jupiter's weather, it explores its structure, origin, and evolution, giving us clues about how gas giants form in our solar system and beyond. And in unraveling Jupiter's mysteries, Juno reminds us of the scale and complexity of planets we once thought we knew, and how much more they still have to teach us. It sounds simple enough. Space and time, two everyday words we think we understand. But in the 20th century, physics revealed that these two are not separate, they are one. Space-time is the fabric of reality. It's the stage upon which everything in the universe plays out, from drifting dust to colliding galaxies. And it's not just a metaphor. It has structure, geometry, and as Einstein showed, it can bend. Before Einstein, time was thought of as absolute, a universal clock ticking the same for everyone. Space, too, was simply the emptiness in which things happened. But in 1905, with special relativity, Einstein showed that time is not fixed. It can stretch and compress depending on how fast you're moving, and space can do the same. Then, in 1915, with general relativity, Einstein went further. He proposed that mass and energy curve space-time, and that curvature is what we perceive as gravity. Imagine placing a bowling ball on a trampoline. The fabric dips under its weight. Now roll a marble across the surface. It curves around the dip, not because it's pulled, but because the fabric tells it how to move. That's what gravity is in Einstein's view. The geometry of space-time itself, directing the motion of planets, stars, even light. But this fabric is not made of threads or particles. It's a set of relationships between locations and moments described by mathematical rules. It stretches, it flexes, it evolves. When massive objects accelerate, say when black holes collide, they send ripples through space-time. We call these gravitational waves. Understanding space-time changed physics forever. It blurred the line between what is and when it happens. Every second that passes, every step we take, is woven into a larger whole. You don't move through space. You move through space-time, a four-dimensional landscape where past, present, and future are connected. And while we live within this fabric, we're still learning its shape, its texture, and its secrets. In 1915, Albert Einstein did something extraordinary. He rewrote our understanding of gravity, not as a force pulling objects together, but as the result of how mass and energy bend the geometry of space-time. That's the heart of general relativity. To grasp it, start with a simple question. Why does the Earth orbit the Sun? For centuries, we thought it was because of a gravitational force, an invisible pull between two massive objects. But Einstein offered a different picture. In his view, the Sun curves the space-time around it, and Earth isn't being pulled, It's moving along the straightest possible path in this curved geometry, like a marble rolling along a dimpled sheet. Earth simply follows the contours of the space-time landscape. This idea was radical because it meant that space and time aren't just passive backdrops. They are dynamic, shaped by what's in them, and in turn shaping how everything moves. To express this, Einstein created a set of equations, the Einstein field equations. They're complex, but they boil down to this: mass tells space-time how to curve, and space-time tells matter how to move. One of the first tests of the theory came in 1919 during a total solar eclipse. Astronomers measured the position of stars near the sun and found that their light had bent as it passed by. Einstein's predictions were correct. That bending of light, called gravitational lensing, has become one of the most powerful tools in modern astronomy. We've used it to find dark matter, measure cosmic expansion, and peer deep into the early universe. General relativity also predicted the existence of black holes, regions where space-time curves so steeply that not even light can escape. And it laid the groundwork for our understanding of cosmic evolution from the Big Bang to today. Despite its age, general relativity remains one of the most accurate theories in science. Time and again, it has been tested in GPS satellites, in the orbits of Mercury, in the detection of gravitational waves. It's a theory that didn't just change physics, it changed how we see reality, not as a static arena, but as a living, warping fabric in motion with the universe itself. We tend to think of time as steady, a constant rhythm ticking forward for everyone. But Einstein showed that time is not absolute. It can slow down or speed up, depending on where you are and how fast you're moving. This effect is called time dilation, and one of the most surprising causes of it is gravity. According to general relativity, the stronger the gravitational field you're in, the more space-time curves, and the more time slows down. This is called gravitational time dilation. It's not just theory. It's been measured with atomic clocks placed on mountaintops and in orbit. The results are clear. Clocks closer to Earth's surface tick more slowly than those farther away. So yes, if you live at sea level, you age ever so slightly slower than someone living in the mountains. The effect is tiny on Earth, just billionths of a second per year. But in stronger gravitational fields, like near a neutron star or black hole, time slows dramatically. Near the event horizon of a black hole, it can nearly stop. Even in our daily technology, time dilation matters. GPS satellites, which orbit Earth at high altitudes and speeds, experience both gravitational and velocity-based time dilation. Their onboard clocks tick faster than ground clocks, and without correction, GPS location data would become inaccurate by kilometers every day. Imagine this: an astronaut orbiting Earth for 6 months ages a fraction of a second less than people on the surface. If they traveled near a black hole or at near light speed, the difference would be much more extreme. This isn't science fiction, it's a built-in feature of reality. Time is elastic. It bends to gravity. And with every tick of every clock, the universe is reminding us where you are and what's around you shapes how fast time flows. In space, the clocks tell different stories, and some of those stories are slower than ours. Imagine this: 2 identical twins. One stays on Earth, the other boards a spaceship, accelerates to near the speed of light, travels for years, then returns. When they reunite, something astonishing happens. The twin who traveled is younger. This is the essence of the twin paradox, one of the strangest predictions of Einstein's theory of special relativity. But it's not really a paradox at all, just a consequence of how time behaves at high velocities. When an object approaches the speed of light, time for it slows down relative to an outside observer. This means that from Earth's point of view, the traveling twin's clock ticks slower, and when they come back, less time has passed for them than for their sibling. The effect is not symmetrical because the traveling twin changes frames, accelerating, turning around, and decelerating, while the earthbound twin does not. That switch makes all the difference. This isn't just thought experiment material. Particles called muons, created in Earth's upper atmosphere, decay rapidly. But when they move at near light speed toward the surface, they last longer than expected, because from their perspective, time slows down. We've observed this many times, so in principle, time travel to the future is possible. We can't do it yet on a human scale, but the laws of physics allow it. What about time travel to the past? That's a more difficult question. Some solutions to Einstein's equations, like closed time-like curves, suggest it might be possible under extreme conditions, near rotating black holes or using hypothetical structures like wormholes. But those ideas remain speculative. They often involve exotic matter, negative energy, or violate causality, the fundamental rule that causes precede effects. Still, the twin paradox reminds us that time is not fixed. It's relative, shaped by motion and gravity. And the faster you go, the less of it you experience. In a universe where time is stretchable, one truth remains. The clock is not the same for everyone, and for some, the future comes faster. We've grown used to the idea that mass bends space-time, but under certain conditions, mass doesn't just bend it, it twists it. This strange effect is called frame dragging, and it happens when a massive object spins. Imagine space-time as a pool of thick honey. Now drop a heavy spinning ball into it. Not only does the ball create a dip, it also causes the honey nearby to swirl around. That's what a rotating planet or star does to the space-time around it. It drags it along with its rotation. This idea was first predicted by Austrian physicists Joseph Lenz and Hans Thirring in 1918, just a few years after Einstein published General Relativity. But it took nearly a century to prove it. In 2004, NASA launched Gravity Probe B, a satellite equipped with ultra-precise gyroscopes. It orbited Earth and measured how its rotation pulled on local space-time. After years of analysis, the results were clear. The gyroscopes had shifted ever so slightly, just as general relativity predicted. This means that near a rotating object, the very coordinate system of space and time is being twisted. And this isn't just an abstract curiosity. Near extreme objects, like neutron stars or spinning black holes, frame dragging becomes incredibly strong. A region called the ergosphere forms around a rotating black hole where nothing can remain still. Even light is forced to co-rotate with the black hole's spin. This twisted space-time could, in theory, be harnessed. Some physicists have proposed using the rotational energy of black holes as a cosmic battery, drawing energy from the ergosphere using clever physics. Frame dragging also plays a role in pulsar timing, accretion disk behavior, and even the dynamics of gravitational waves. It's a reminder that space-time isn't a flat stage. It flows, it turns, and where mass spins, the very fabric of the universe spins with it. In the silent void of space, a new kind of signal is traveling. It's not light, it's not sound, it's the vibrations of space-time itself. These are gravitational waves, ripples in the fabric of the universe, caused by the acceleration of massive objects. Einstein predicted them in 1916 as a consequence of his general theory of relativity. But he doubted we would ever detect them. They seemed too faint, too subtle, too far beyond human reach. For a century, they remained a theoretical whisper. Then, in 2015, The whisper became a roar. Scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, detected a fleeting signal. Two black holes, each dozens of times more massive than our sun, had spiraled into each other over 1 billion years ago. The collision sent shock waves through the cosmos, and when those ripples reached Earth, they stretched and squeezed space by less than the width of a proton. But LIGO was sensitive enough to see it. Since then, dozens of gravitational wave events have been recorded: black hole mergers, neutron star collisions, cosmic cataclysms unfolding in total darkness. Some of these events produce light, others don't. Gravitational waves let us hear what telescopes cannot see, and this new kind of astronomy is just beginning. Unlike light, gravitational waves are unblocked by dust or gas. They pass through everything. They let us peer into regions hidden from traditional telescopes, the hearts of supernovae, the cores of merging galaxies, the first seconds after the Big Bang. Soon, new detectors, like LISA, a space-based gravitational observatory, will open even wider windows into the universe. We used to think of the cosmos as silent, but now we know. It rings like a bell, with each massive collision sending echoes across eternity. And when we listen, really listen, we don't just observe the universe, we feel its movements, not through sight, but through the trembling of space itself. When we look into the night sky, we see galaxies, hundreds of billions of them, scattered across the vast darkness. But those galaxies aren't just sitting still. They're moving away from us, and not because they're traveling through space, but because space itself is expanding. This idea, the expanding universe, is one of the most profound discoveries of modern cosmology. It began with the work of Edwin Hubble in the 1920s. He noticed that distant galaxies had light that was redshifted, stretched toward longer wavelengths. The farther away a galaxy was, the more its light was redshifted. The conclusion: the universe is growing. But what does that really mean? Here's where the balloon analogy comes in. Imagine a balloon with tiny dots drawn on its surface. As you blow it up, the surface stretches, and as it stretches, each dot moves away from the others, not because the dots are moving themselves, but because the surface they rest on is expanding. Now think of the universe as that balloon, only in 3 dimensions. Galaxies aren't flying through pre-existing space. They're being carried apart as space itself stretches. This expansion happens everywhere, not just at the edges. In fact, there are no edges, just more space unfolding. And this insight leads to something even more surprising. If the universe is expanding now, then in the past, it must have been smaller and denser and hotter. This is the foundation of the Big Bang Theory. But the expansion isn't slowing down, it's speeding up. Thanks to a mysterious force called dark energy, space is stretching faster and faster over time. In the far future, galaxies beyond our local group will drift so far away that their light will no longer reach us. The night sky will grow darker. Cosmic history will fade from view. The balloon keeps inflating, and we, on one small dot, are watching the surface grow. The Big Bang tells us that the universe began from an incredibly hot, dense state. But there's a twist to that story, a brief moment far earlier than what we usually picture, when the universe expanded faster than the speed of light. This is called cosmic inflation. It happened in the tiniest fraction of a second after the Big Bang, around 10 to the negative 36 power seconds. During this blink of time, the universe doubled in size again and again, ballooning outward at an astonishing rate. Not because matter was flying through space at impossible speeds, but because space itself was expanding faster than light. That sounds like it breaks the rules, doesn't it? But it doesn't. Einstein's theory says nothing can travel through space faster than light, but space itself can expand at any speed. And during inflation, it did. Why do scientists believe this happened? Because inflation solves several cosmic puzzles. First, the horizon problem. Why is the universe so uniform, with the same temperature everywhere, even in regions that could never have exchanged light or energy? Inflation suggests those regions were once connected before being stretched far apart. Second, the flatness problem. Why does the universe seem so perfectly geometrically flat? Inflation smoothed out any early curvature, like a balloon surface stretching smooth as it grows. Third, inflation helps explain the seeds of structure. Tiny quantum fluctuations during inflation were magnified to cosmic scales, becoming the foundation for galaxies, stars, and clusters. Though inflation is still a theory, it matches observations remarkably well, especially the cosmic microwave background, a faint afterglow from the early universe. We may never directly see inflation. It happened too fast, too early, too far beyond light's reach. But its fingerprints are etched across the sky. A moment when the universe, barely born, took a breath so vast that everything we know came rushing into existence. At a speed no particle could match, but space itself could. When we gaze into the night sky, we're not just looking across space, we're looking back in time. The farther away something is, the older the light we see. And with powerful telescopes, we can now observe galaxies whose light has been traveling for over 13 billion years. But there's a limit to how far we can see, not because the universe has an edge, but because light itself has a limit, the speed at which it travels. This limit defines what we call the observable universe, a sphere centered on us, stretching about 46 billion light years in every direction. Wait, 46 billion? How is that possible if the universe is only 13.8 billion years old? Because while light was making its way to us, space itself was expanding. So the objects that emitted that ancient light are now much farther away than they were when the light first left them. What lies beyond the observable universe? Most scientists believe the cosmos continues far past what we can seize, perhaps infinitely far. But beyond that edge, light hasn't had time to reach us yet. It's not a boundary in space, but invisibility. And here's something even more humbling. As the universe expands faster and faster, distant galaxies are receding at ever-increasing speeds. Some are already moving away from us faster than light, not by motion, but by the stretching of space. Their light will never reach us. They are permanently beyond our cosmic horizon. In time, more and more galaxies will cross that line. The observable universe will shrink, not in size, but in content. Eventually, we may find ourselves in a lonely sky, with only a few nearby galaxies still in view. So when we look at the deep field images from telescopes like James Webb, we're seeing not just the ancient universe, we're seeing the most distant pages of a story we'll never fully finish. A silent horizon surrounds us, beyond which the light has not and may never arrive. Time feels like the most basic thing there is. It flows, it ticks, it separates the past from the future. We wake, we sleep, we age, and time moves forward. But what if time isn't real? Not in the way we think. In physics, time is surprisingly slippery. In Einstein's universe, time is just one coordinate in the fabric of space-time. Not absolute, but relative. It bends near gravity, stretches at high speed, and passes differently depending on where you are. That alone is unsettling. But some physicists now go even further, suggesting that time may not be fundamental at all. Instead, it may be emergent, a feature that appears when many particles interact, like temperature emerging from the motion of atoms. At the deepest level, in quantum gravity or string theory, time may not exist in any meaningful way. Some equations describing the universe don't even include time as a variable. The famous Wheeler-DeWitt equation, a candidate for describing quantum spacetime, is timeless. It describes a universe that simply is, not one that unfolds. This leads to strange questions. If the fundamental laws don't include time, why do we experience it so vividly? Why do we remember the past but not the future? Why does entropy, disorder, increase? Some researchers believe entropy is the key. The flow of time may be a reflection of the universe's journey from order to chaos. We perceive time moving forward because we live in a universe where entropy increases. Others suggest that our experience of time is rooted in consciousness, in memory, in the way our brains track change. But if time isn't fundamental, what replaces it? Perhaps a landscape of possible configurations, a giant map where moments don't follow one another. They simply exist, side by side, like pages in a book, all already written. In such a view, the future doesn't happen. It is. And the past isn't gone. It still exists. Time, then, may be an illusion, but one we cannot live without. If you drop a glass and it shatters, you don't expect the shards to leap back together. A fire burns wood to ash, not the other way around. Milk mixes into coffee but never unmixes. These are all signs of one universal truth. Time has a direction. It moves forward, but why? Physics is mostly time symmetric. The laws that govern atoms and gravity don't care whether time flows forward or backward. But in our everyday world, time clearly has an arrow. The reason lies in a single word: entropy. Entropy is a measure of disorder, or more precisely, the number of ways a system can be arranged. A neatly stacked deck of cards has low entropy. A shuffled deck has high entropy. There are more messy states than ordered ones. In thermodynamics, systems naturally evolve toward higher entropy. That's the second law, and it's why time flows in one direction, because the universe is moving from order to chaos. At the beginning of the universe, entropy was incredibly low. The cosmos was hot and dense, but remarkably uniform. Since then, stars have formed and died, galaxies have collided, black holes have grown, and entropy has skyrocketed. The arrow of time, then, is a thermodynamic arrow. It points from the smooth past to the messy future. But this raises a deep mystery. Why did the universe begin in such a low entropy state? It's still one of the biggest questions in cosmology. If we rewound the universe, let entropy decrease, everything would move in reverse. We'd unbreathe air. We'd remember tomorrow instead of yesterday. But in our real experience, memories are linked to entropy. So are cause and effect. We act before results, not after. Entropy, then, doesn't just shape stars and galaxies. It shapes our sense of time itself. Without it, past and future would be meaningless. There would be no direction, only stillness. But with it, time marches on, one messy moment after another. We often think of relativity as something abstract, a theory for black holes and distant galaxies. But it's not just the stuff of physics textbooks. It's in your pocket. Every time you use GPS to navigate traffic, find a coffee shop, or call a ride, you're relying on Einstein's ideas. Here's how. GPS satellites orbit the Earth at an altitude of about 20,000 kilometers. Each carries an atomic clock, accurate to a billionth of a second. These clocks constantly broadcast signals that your phone receives and uses to calculate your exact position. But there's a problem. Time doesn't flow the same everywhere. Because the satellites are high above Earth, they experience weaker gravity, which, according to general relativity, means their clocks tick faster than clocks on Earth. At the same time, the satellites are moving fast around the planet, and according to special relativity, that motion causes their clocks to tick slower compared to a stationary observer. The result? A mismatch. The gravitational effect makes the satellite clocks run about 45 microseconds faster per day, while their speed slows them down by about 7 microseconds. Combined, they gain 38 microseconds each day relative to clocks on the ground. That might sound tiny, but without correction, it would throw off GPS measurements by kilometers in just a day. So what do engineers do? They build relativity into the system. GPS satellites are pre-programmed to tick slightly slower, so that once in orbit, their time aligns with Earth's. It's one of the most practical proofs of relativity. Without Einstein's insights, your navigation apps wouldn't work. Your plane wouldn't fly the right route. Precision farming, disaster response, financial systems all rely on this subtle synchronization. So the next time you get directions, Remember, you're not just using technology. You're using a theory forged in 1905, proven in 1915, and orbiting the Earth today. Relativity isn't just real, it's essential. Imagine a mass greater than our sun, crushed into a sphere just 20 kilometers wide. That's a neutron star. It's one of the strangest objects in the universe, and what happens inside it defies our everyday understanding of matter, pressure, and time. A neutron star is born in death. When a massive star runs out of fuel, it can no longer resist the inward pull of gravity. Its core collapses, and if it's not quite massive enough to become a black hole, it compresses into something else, a ball of pure nuclear matter. The gravity is so intense that electrons are forced into protons, creating neutrons, hence the name. The result: a city-sized object with a density so extreme that just a teaspoon of neutron star material would weigh 1 billion tons. But what's really inside? We don't fully know. The outer crust is made of iron and super-dense atomic nuclei. Deeper in, atoms no longer exist as we know them. Only a sea of neutrons, packed tighter than anything found on Earth. Some theories suggest that at even deeper levels, the neutrons break apart into quarks, the fundamental building blocks of matter. If so, the core could contain quark matter, or even a form of exotic strange matter, denser than anything else in the known universe. And then there's the magnetic field. Neutron stars often spin rapidly, sometimes hundreds of times per second, and some emit beams of radiation that sweep across space like a cosmic lighthouse. We call these pulsars. Their magnetic fields can be 1 trillion times stronger than Earth's. They can bend particles, warp light, and tear atoms apart. The surface, it's just a few centimeters thick. But the gravity is so strong that a fall from 1 meter would hit you at thousands of kilometers per hour. Time itself slows down near such gravity. Even though it's not a black hole, a neutron star's mass bends space-time profoundly. So what happens inside a neutron star? It's one of the biggest mysteries in physics, a natural laboratory of forces we can't yet replicate, holding answers about matter, energy, and perhaps even the origin of everything. In the quiet heart of a dead star, reality itself is rewritten. Time feels like it flows in one direction. Moments pass, memories form, and the future stays just out of reach. But is that direction forward, built into the universe? Or could time, under the right conditions, actually run backward? Let's start with the physics. The fundamental laws of nature, the ones governing motion, electricity, gravity, and quantum particles, are mostly time symmetric. That means if you filmed the universe and played it in reverse, the equations wouldn't complain. They'd still hold true. But in our daily lives, time feels very different. Eggs don't unscramble. Smoke doesn't return to a fire. Memories don't form from the future. This one-way flow is called the arrow of time. Where does it come from? The answer lies in entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy tends to increase over time. It's why hot coffee cools down, but never heats back up on its own. Why things break, but don't unbreak. This statistical rule gives time its direction. But here's the strange part. Nothing in the fundamental laws requires low entropy in the past. So why did the universe start in such an ordered state? No one knows for sure. Some physicists believe that the arrow of time is not fundamental, that it emerges from boundary conditions like the smooth, low entropy state of the Big Bang. Others suggest that if you zoomed out far enough, time might look like a loop or even run differently in other parts of the cosmos. In quantum mechanics, things get even weirder. Some interpretations suggest time doesn't flow at all, that it's just a way for us to describe correlations between events. And yet, we feel it. We age. We remember. We act in the present, not the past. Could time reverse? Mathematically, yes. Physically, maybe, under extreme or hypothetical conditions. But for now, in this part of the universe, time still moves forward, 1 second at a time. Even if the equations don't care, we do. Nikola Tesla is remembered as one of the most brilliant inventors of the modern era, a pioneer of electricity, radio, and wireless communication. But beyond his concrete achievements, Tesla also had deeply unconventional ideas about time, energy, and the universe itself. In his later years, Tesla began to speak and write about vibrations and frequencies as the keys to understanding all reality. He once said, "If you want to find the secrets of the universe, think in terms of energy, frequency, and vibration." To Tesla, time was not a simple ticking clock. He viewed it more like a dimension of resonance, a field shaped by invisible forces. He believed that just as we could tune into specific frequencies in sound or light, perhaps one could tune into different moments and times, or even redirect its flow. Tesla also speculated that all matter was composed of subtle vibrations. In his vision, every object, even every thought, had a frequency, and in a universe of perfect resonance, time might not be a river flowing one way, but a pattern that could be reshaped. These ideas often brought him into conflict with the mainstream physics of his day. While Einstein was formalizing space-time and relativity, Tesla was exploring ether, scalar energy, and nonlinear time, using the language of intuition and electrical engineering more than formal equations. Some of Tesla's most speculative work involved machines that could transmit energy through space, devices he claimed could alter weather, heal the body, or even disrupt time. None of these were ever proven, but his notes, interviews, and unpublished patents have fueled decades of fascination and conspiracy theories. Did Tesla really understand something others missed? Or was he simply dreaming beyond the limits of science? Today, physicists study gravitational waves, quantum fields, and the fabric of space-time. They use tools Tesla could never have imagined, but chase questions he once asked. And while many of his views on time remain outside accepted science, Tesla's core insight that the universe is alive with frequency and energy echoes through modern physics, from string theory to quantum mechanics. He may not have built a time machine, but in many ways, Tesla was always thinking ahead of his time. Every story has an ending, even the universe. But how does time itself end? Cosmologists have proposed several possibilities, and two of the most compelling are the heat death and the Big Crunch. Each tells a different story about the ultimate fate of time, space, and everything we know. Let's begin with the heat death. This is not an explosion, but a slow fading. In this scenario, the universe keeps expanding forever. Galaxies drift apart, stars burn out, and black holes slowly evaporate. Over trillions of years, all motion winds down. Why? Because of entropy. As energy spreads out and systems reach equilibrium, there's less and less free energy to do work. Eventually, all temperature differences vanish. No more stars, no more life, no more change. The universe becomes cold, dark, and quiet. A sea of particles drifting through nearly empty space. Time, in a sense, loses its meaning because nothing happens anymore. That's heat death. A final whisper, not a bang. But there's another possibility, the Big Crunch. If the universe contains enough matter, gravity could one day overcome expansion. Galaxies would stop drifting apart, and begin falling back together. Space would contract, temperatures would rise. Eventually, all matter and energy could collapse into a single point, a mirror of the Big Bang in reverse. Time might run backward near the end, or it might end entirely, crushed under infinite density. Some theories even suggest the Big Crunch could trigger a new Big Bang, a cyclical universe, forever collapsing and rebirthing. But current observations show the universe's expansion is accelerating, driven by a mysterious force called dark energy. This makes the heat death more likely for now. Still, both endings force us to confront a haunting question. If time had a beginning, can it also have an end? And if everything stops, does that mean time itself ceases to exist? Or does the fabric of reality simply wait, quietly stretched, forever expanding into silence? Imagine standing near the edge of a black hole, not inside, but just above its event horizon. To you, time seems normal. Your heart beats, your thoughts unfold, your clock ticks second by second. But to someone watching from far away, you appear frozen. This is gravitational time dilation at its most extreme. According to Einstein's theory of general relativity, the stronger the gravity, the slower time passes. And nothing warps gravity more than a black hole. At the edge of a black hole, the event horizon, space is so curved that light can't escape. And as you approach it, your time begins to stretch from an outside perspective. If you hovered just above the horizon, your seconds might become minutes to someone at a safe distance. Hover closer, and those minutes could become years. This isn't science fiction. It's been confirmed, not near black holes, but in more modest ways. Astronauts in orbit age slightly slower than people on Earth, thanks to both their speed and weaker gravity. On Earth, GPS satellites have to account for time dilation to stay accurate. If they didn't, your phone's location would quickly drift off course. But near a black hole, the effect is magnified. In the movie Interstellar, a team lands on a planet near a massive black hole. Because of its intense gravity, every hour on the surface equals 7 years back on their ship. The science behind that scene is surprisingly sound, a real extrapolation of Einstein's equations. This leads to haunting ideas. If you could survive close enough to a black hole, protected by technology we don't yet have, you might experience a few days, while centuries pass for the rest of the universe. Black holes don't just distort space, they pull on time itself, stretching it thin. So next time you imagine a clock ticking, picture it bending slowly under the immense weight of a collapsed star, because near a black hole the universe waits. And so do you. What if two distant places in the universe were connected, not by endless space between them, but by a tunnel? That's the idea behind a wormhole. It sounds like science fiction, and often is. But the concept has its roots in real physics, first proposed in 1935 by Albert Einstein and his colleague Nathan Rosen. They were working on general relativity when they discovered that under certain conditions, space-time could contain a kind of bridge, a shortcut between two regions. They called it an Einstein-Rosen bridge. Today, we call it a wormhole. Imagine space as a two-dimensional sheet. If you fold it and punch a hole through, you can move from one point to another instantly, skipping the vast distance in between. That's what a wormhole offers, a way to travel across the cosmos faster than light, not by exceeding the speed limit, but by taking a shorter route. But there's a catch, or several. First, wormholes are incredibly unstable. They tend to collapse before anything, even light, can pass through. To keep one open, you'd need something exotic, matter with negative energy density, the kind that might violate known physics. Second, even if a wormhole existed and stayed open, it might not be traversable by humans. Tidal forces near the throat could tear you apart. And third, there's the problem of causality. Some solutions suggest that wormholes could be used for time travel, allowing a traveler to emerge in the past. That raises all kinds of paradoxes, like the famous question, what happens if you go back and prevent your own birth? Still, wormholes remain a tantalizing possibility. They appear in the equations. They inspire movies and thought experiments, and in the quest for a unified theory of quantum gravity, some researchers believe wormholes may offer clues to how space and time are woven together. So far, no evidence of a wormhole has ever been found. But if one ever were, it could change not just our understanding of space, but of time, reality, and distance itself. We often imagine empty space as truly empty, a vast, silent void. But in the world of quantum physics, even nothing is something. Zoom in far enough, and what seems smooth becomes turbulent. At the smallest possible scale, the Planck length, space-time itself starts to froth and jitter. This is what physicist John Wheeler called quantum foam. Picture the surface of a calm ocean from a great distance, smooth and glassy. But up close, It's a storm of ripples, waves, and chaos. Quantum foam is like that, the fine-grained texture of the universe, too small for us to see, but not too small to matter. At this scale, a trillionth of a centimeter, the certainty of position and time breaks down. Particles pop in and out of existence. Energy fluctuates. Even the geometry of space itself may flicker, twisting, curling, maybe even briefly forming baby black holes or microscopic wormholes before collapsing again. It's like reality is boiling underneath our perception. This frothy understructure is believed to be the arena where quantum gravity rules, a realm where Einstein's smooth space-time and quantum mechanics finally meet. We don't yet have a theory that unifies them, but approaches like loop quantum gravity and string theory try to describe this granular fabric. Some suggest that space is quantized, made of discrete units like atoms of geometry. Others think that space and time may not even be fundamental, just emergent properties of deeper quantum relationships. But why does this matter? Because the nature of this foam may hold the key to understanding everything. Black holes, the origin of the universe, even the fate of information. The quantum foam might be the raw material from which space, time, and energy all arise. A seething chaos beneath the calm surface of reality. We can't see it yet, but its presence is whispered in equations, hinted at in experiments, and dreamed about in the minds of physicists. In the quiet fabric of nothing, everything may be waiting. When we gaze into the night sky, the universe feels endless. But is it truly infinite? And more importantly, what shape does it have? This isn't just a philosophical question, it's one of geometry, and the answer changes how we understand space, time, and the cosmos itself. There are three possibilities. The first is that the universe is flat. In this geometry, parallel lines never meet. Triangles add up to 180 degrees. It stretches on forever in all directions. This is the universe that fits best with Einstein's general relativity and most modern measurements. Then there's a closed universe, like the surface of a sphere. If you travel far enough in one direction, you might return to where you started. There are no edges, but the total space is finite. It would imply a universe that could one day stop expanding and collapse in a big crunch. The third option is an open universe, saddle-shaped. Here, space curves away from itself. Parallel lines diverge. It still expands forever, but in a geometry that feels stretched and cold. So which is it? The answer lies in the cosmic microwave background, the faint glow left from the Big Bang. By studying its tiny fluctuations, scientists can measure the curvature of space, and what they've found is remarkable. The universe appears to be flat, to within a very small margin of error. Not perfectly flat, but so close that any curvature would have to exist far beyond the observable universe. This has deep implications. A flat universe supports the theory of cosmic inflation, a rapid expansion in the first fraction of a second after the Big Bang. It also hints that the cosmos might be infinite, or at least so large that we'll never see its edges. But geometry isn't the only mystery. Even in a flat universe, space can bend and twist locally due to gravity. Galaxies, black holes, and dark matter warp the nearby fabric, shaping everything from light to time itself. So while the global shape may be flat, the local landscape is anything but smooth. The universe may not be a sphere, or a saddle, or a loop. It may be a vast, expanding flatland, with endless room for stars, for time, and for questions